So let's now move on to the other internal effects that we have to check in order for us to properly design a flexural member. So from the previous topics, we have discussed the capacity of a flexural member in resisting flexural stresses. So we have found out that the maximum moment that a flexural member can withstand given a certain magnitude of transverse loading is just equal to the plastic moment, which is just the product of the yield stress and the plastic modulus. Okay, so you have to take note that a beam doesn't experience only flexural stresses. Our beam is not only subjected to bending moment as an internal effect, but also it is also subjected with shear forces. Okay, because if you can remember, if we have a beam, say for example a simply supported beam loaded by a certain magnitude of load, say a point load there, we know for a fact that the effect of this load on the beam is not only to induce bending moment but also shear forces. As you can remember from strength of material or mechanics of deformable bodies, there are uh, there are shear forces that will be induced inside a beam. Say, for example, it is loaded by a uniformly distributed load like this all throughout its length. The 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 variation of shear forces along the length of the beam will look something like this. Okay, and then the corresponding bending moment that will be experienced by the beam inside it looks something like this. So this is what you these are what you call the shear and moment diagram of the singly supported beam. So you can see here that a transverse load doesn't induce only bending moment alone, but there's always a corresponding shear forces along with the introduction of bending moment. So from the previous topic, we just discussed about the maximum moment, which is this, that can be withstand or resisted by a flexural member. And again, we have known that that capacity with respect to moment or flexural stresses or bending is just equal to the plastic moment, which is the product of Fy and Z, the yield stress and the plastic modulus. So this is the bending moment. This is the maximum bending moment that the beam can withstand before the whole cross section will yield. Before the whole cross section will experience a stress larger than the yield stress. Okay, so that is the topic that we have discussed from the previous discussion. So for now, for this topic, we will now move on to the next effect that we have to consider whenever we design flexural members, which is the shear effect. This we will focus here on the shear effects that are induced inside a flexural member. So from mechanics of deformable bodies, the flexural shear stress at a point in the beam cross section is determined to be equal to this. So this is the formula for finding the shear stress along any point on the cross section of a beam. Say for example, if you have a rectangular beam with a neutral axis located here and a if we want to find the shear stress on any point here, say for example, the shear stress on this particular point, all we need to do is use this formula. So what is the formula all about? So the formula is just equal to VQ over IB. The shear stress is just equal to VQ over IB, wherein FB is the flexural shear stress, V is the shear force acting on the beam cross section, Q is the first moment of area of the region between the point of interest and either the topmost or bottommost part of the cross section about the neutral axis. I is the moment of inertia of the beam cross section about the neutral axis, and B is the width of the cross section at the point of interest. So just to have a quick recap on how to compute or how to use the formula for finding the flexural shear stress on a cross section of a beam. Say for example, we are considering a certain point here. We want to find the shear stress on this particular point. On wait, reviewing mechanics of the formable bodies, we have found out there on the subject that the shear stress on this particular point is just the same as the shear stress on this particular point, or any point with the same distance from the neutral axis. We have found out that concept way back from mechanics of the formable bodies. We have known that the flexural shear stress being experienced on the cross section are just equal if they have the same distance from the neutral axis. Okay, so meaning if you are considering the flexural shear stress of this particular point, it's just like the same as considering the flexural stress acting on this uh, whole part of the cross section. Okay, so how do we compute the magnitude of the shear stress on this particular part of the cross section? So first, we need to have the demand, the shear force V that is acting along the cross section. And then we need the I, the moment of inertia. So we know how to compute the moment of inertia with respect to the neutral axis. B is the width of the particular part of the cross section that you want to investigate the flexural shear stress. So say for example, in this particular case, this is what we call B. This is the width. This is the width of the certain portion of the cross section that we want to investigate the shear stress. And then lastly, Q is the statical moment of area, which is just the moment of the area between this line and the nearest extreme fiber. So on this particular point, since this is the line that we are concerned, and the nearest extreme fiber is this, therefore the area that we will be considering is this. So all we need to do is get the moment of this area with respect to this neutral axis. Okay, so we just have to multiply the area to this certain distance. Let's call this D. Okay, so we just need to multiply this area to the distance of its centroid. So you have to remember that the moment arm must be from the centroid of this area to the neutral axis. So just multiply the area with this moment arm, and then you will easily get the statical moment of area. Okay. So and then after you have gathered these parameters, all you need to do is substitute to this corresponding formula, and then you will already be able to compute for the shear stress on this particular point or region on the cross section of a rectangular beam. Okay. For the case of a beam an with an I section like this, so the cross section looks something like this. It is made up of an I beam like this one. So for this particular case, if this is the shear force acting on that cross section, if you want to find the variation of shear stresses from the extreme top fiber to the extreme bottom fiber, the variation of shear stress along the depth of the beam will look something like this. Okay, so you can see here, most of the shear stress is actually acting on the web. So the main component of the cross section that resists the shear stress is actually the web, as depicted here on this diagram. Okay, so you can see here this portion of the diagram acts on the web. So that is the shear stresses acting on the web. While this very small portion here and here are just the shear stresses acting on the flanges. So you can see here that the shear stresses acting on the flanges are just very small compared to the shear stresses acting on the web. Therefore, we can say that the main the main component of the cross section that resists shear stresses is actually the web. Okay, so why is that? Why is it that the shear stresses acting on the flange uh, is relatively small compared to the web? So the reason for that is the use of this formula. Okay. So the main reason there is uh, the statical moment of area, the Q, the Q. That's the main reason there. Because as you can see here, if we will be computing for the statical moment of area of a point here located here on the interface of the flange and the web, the area that we will moment to the neutral axis will just be equal to this. Okay, which is very small compared to the area if the location that we are interested is located somewhere on the web. If we are concerned with the shear stress on this particular line, we have to get the moment of the area from this point up to this point. So the area will be equal to this. Just change the color. So this is the area that we have to get the moment. If we are concerned with the shear stress acting on this particular point, so obviously on this figure you can easily infer that every point along the web will have a larger statical moment of area compared to any point that is located along the flange. Okay, so because of that, this variation of shear stress happen. Okay, so for flexure, the opposite happens. That the flanges are the main resisting component of the moment. Okay, because as you can remember, the 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 bending moment acting on the cross section is being resisted by couple couple forces acting on the upper portion and acting on the lower portion. Okay, so the location of these two forces are actually dependent on the magnitude of the flange area. So if we have a larger flange area, therefore this force will tend to move up, and then this force will tend to move down, resulting to greater moment arm. Okay, so if we have a greater moment arm, since the formula for moment is just equal to force times distance, even if we have a constant force, constant magnitude of force here, but since the moment arm increases, therefore the moment capacity increases. Okay, and that result will just happen if the flange area will increase. Therefore, with respect to flexure, with respect to resisting bending moment, the main section component that resists moment are the flanges, while the main component that resists shear stresses or shear forces is the web. Okay, so you have to remember that. For rolled eye sections, it is observed that most of the shear force is carried by the web of the cross-section. Additionally, the maximum flexural shear stress occurring at the cross-section and the average flexural shear stress of the web does not differ by much. Due to this, the shear capacity of a rolled eye section is determined as equal to this. So you can see here, we uh, we should have almost neglected the shear stress acting on the flange. Okay? Although in this particular formula, as you can see, the area of the web that we are talking about here is not the area of the web alone. So it's not from here to here only, but the whole depth was used. Okay? So therefore, the shear area that we are talking about here on this particular formula is actually this area. So if this is the beam, this is the I beam, the shear area, the AW that we are talking about there, is not only this area of the web, but we also included this portion, the flange. Okay, so that is the shear area that we theoretically expect that will resist shear stresses. Okay, so meaning we assume that this shear stress acting here will actually extend on this portion of the flange. Okay, So we use that we 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 use that concept since the average shear stress here, if we will try to find the average, so you can see here the shear stress is acting on the web is not actually constant. If we will try to find its average, so it will be located somewhere here at the middle. The magnitude of the resultant of that shear stress, average shear stress, is almost equal to this diagram if you will just include the flange. So therefore, it was a uh, it was theoretically correct to consider this portion of the of the flange to resist shear stresses. Okay, so where did this formula came from? So again, that just came from the formula for shear stress. Shear stress tau is just equal to V over A. Cross multiply cross multiply A to the left side of the equation, V will just be equal to shear stress times area, the shear area. On this particular case, the allowable shear stress tau that we assume based on the code is just equal to the 60% of the yield stress. And then the shear area A is again equal to this. We also included the portion of the flange and assume that the shear stress acting here is actually extended until on the extreme portion or extreme fiber of the cross section. Okay, so that is depicted on this formula. Wherein yung D, the D is actually the total depth D. Yan. Okay. So as you can see here, we did not maximize the yield strength, of the steel beam. We just used 60% of the yield strength. Okay, so we gave an allowance or some uncertainty on the allowable shear stress or allowable stress that can be experienced by the cross section. Okay, so you can see here, T is defined. T is the depth of the cross section. TW is the thickness of the web of the cross section. The value of zero point 0.6 comes from von Mises failure theory, which determined that the shear strength of a ductile material is around 60% of its yield strength. Okay, so medyo maliit yung capacity of steel section to resist shear stresses compared to the yield strength. So according to the uh, study of von Mises failure theory, it was found out that the shear stress capacity of a steel section is just 60% of the yield stress or yield strength. That's why we did not use the whole Fy here, but 60% only. Okay. So other than that, other than the flexure and the shear force, other than the bending moment and the shear force that we have considered on the previous topics, we also have to consider what we call the serviceability requirements for beams. So we just uh, our we don't just want our beam to be able to resist flexure as well as shear stress, but we want our beam to be also serviceable. Okay, so what do we mean when we say serviceable? Serviceability of a structural member, which refers to a set of conditions that preserve the function, appearance, and occupant comfort of a structure, may prevail or control in the course of the design process. For beam serviceability factors include deflections and vibrations. So that is what we meant when we say serviceability requirements or serviceable. When we say the structure is still serviceable, it just means that the structure still satisfies a certain set of criteria to 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 give service. I mean to provide the service that is actually expected for it to serve. Okay, so when we say serviceable, we just have certain criteria there. Criteria 1, criteria 2, criteria 3, and so on and so forth, in order for us to say that the structure is still serving its intended purpose. Okay. So one of the criteria there are if the beam still preserves its intended function, its appearance, and occupant comfort. Okay, so sometimes we use these things to say whether the beam or the flexural member is still serviceable or not. Okay, if the beam uh, cannot preserve anymore its function, meaning it cannot resist flexural stresses anymore, or if the beam will experience excessive deflection resulting to the change of its appearance. So from horizontal appearance, it will now be uh, deflected like this. So if the beam will experience like that, if the beam will have that condition, it will have a feeling on the occupants that the beam will be on the verge of failing. Okay, so meaning the appearance of the beam will put the occupants uh, on a fearful condition. It might impose fear on the occupants if the appearance of the beam will look something like this. If the appearance will change from this to this because of excessive deflection. So with that, we can say that the beam is not serviceable anymore. Okay, as well as we can also use the comfort with respect to comfort to tell whether the beam is still serviceable or not. If the beam will uh, impose excessive vibrations, it will not give comfort obviously to the occupants because ikaw ba naman 'di ba every time na lang for example may elevator na nakabit sa isang structure syempre may mga beam na nakakabit din doon. Every time na nag-aakyat panaog yung sa elevator mo, there is a tendency na mag-vibrate yung mga floor mo because of the movement, because of the motion of the elevator. So, obviously, mag-vibrate yung mga floor mo, pero dapat hindi excessive. So, yung vibration na yun, dapat i-consider natin sa design. Dapat, kung mag-vibrate man yung ano natin, yung beam natin, dapat hindi excessive. Okay, so we have to limit that. Okay, we have to limit vibration so that the structure will still give comfort to the occupants. Kasi nga, kung may occupants dyan, tas vibrate ng vibrate, baka nagtatalunan na sila sobrang vibrate ng ng floor, di ba? So, it will not serve its intended for purpose if that will happen. It will not serve its intended for purpose. So, hindi na siya magiging serviceable. So, those are just some of the criteria that we usually use to tell whether the structure or the beam is still serviceable or not. Okay, if it still preserved its function, its appearance, and occupant comfort. So the main way to measure the serviceability of a structure, especially beams, is usually deflection as well as vibration. Although vibration, we don't usually consider that uh, for for uh, for undergrad courses. Okay, so for undergrad courses, we usually just consider the deflection serviceability. Okay, meaning we want our beam to not experience excessive deflection like this because it will impose fear to the occupants. It will give a feeling to the occupants that the beam is on the verge of failure. Okay. So we want to limit the deflection that will be experienced by our beam or flexural member so that it will be still serviceable to the occupants. Okay. Section 512 of 2015 NSCP Volume 1 only states that deflection and vibration effects must be considered in design and should not impair the serviceability of the structure. For beam deflection, service load combinations must be used instead of factored load combinations since deflections are of concern when the structure is in use and not when failure is imminent. So, whenever we compute for the deflection of a beam, as what mentioned here, we don't use the ultimate load, the factored load, yung naka-multiply na sa mga 1.2 dead load, ganyan, plus 1.6 live load. Hindi yan yung in-expect natin na mag-i-induce ng deflection. If you want to compute the deflection of a beam, we don't use that factored load. Ang ginagamit lang natin is yung simpleng sum lang ng dead load tsaka live load. Simply because yan kasi yung mag-i-impose ng deflection sa ano, sa beam natin, 'di ba? Kung ito yung beam natin, paano ba siya magkakaroon ng deflection? Siyempre, kapag meron na siyang nire-resist na load, which is usually coming from the dead load and live load only. So hindi naman yan nagkakaroon ng ano ng amplification. Okay? So gusto nating whenever we compute the deflection, gusto nating makuha ang deflection is yung deflection due to the service loads that are being served or resisted by the beam. Okay? Hindi natin hinahanap yung load or yung condition kung saan ang nire-resist na load ng member is actually an amplified load, yung naka-multiply na sa mga factor 1.2, 1.6 sa live load. Hindi yan yung gusto nating makuha. Hindi deflection ng beam supporting this amplified load yung hinahanap natin, kundi yung service loads lang kung saan meron lang dead load tsaka live load na nire-resist yung beam. Yan lang yung ginagamit natin usually whenever we compute deflection. Hindi yung naka-factor, yung service lot. Okay? Yung wala pang amplification factors. Maximum beam deflections can be determined using classical methods of structural analysis, including but not limited to geometric methods, work energy methods, of deflection method, and moment distribution method. So there are many ways, there are many methods to compute the deflection or maximum deflection that can be experienced by a flexural member such as a beam. Okay, so marami kayong inaral way back structural theory days. Diba? Merong mga geometric methods, work energy methods, slope deflection method, as well as moment distribution method. So ang goal natin dito to check the serviceability of beams is to check what is the corresponding deflection of a beam given a certain load, dead load, and live load acting together. Okay? So hindi natin in-expect yung load as much as this. Okay? Kasi hindi naman natin na check yung condition ng beam on this extreme condition kung saan naka-amplify na yung deflection, yung dead load tsaka yung live load, di naman natin kino-consider. Hindi naman yun yung condition na kino-consider natin dito. Yung condition na naka-amplify na due to some effects, yung mga magnitude ng dead load tsaka live load. Ang kino-compute lang natin na deflection dito is yung deflection kapag meron ng nakatapos dyan na dead load as well as mga live load. Okay? That's why again, take note, hindi factored load yung ginagamit natin whenever we compute deflection. Yung service loads lang, dead load plus live load. And we can compute for the deflection imposed by these loads using different methods. You just have to choose what's uh, what's uh, what what's fit with the given problem, as well as kung anong method yung kaya mo, kung saan ka komportable na method. So yun lang yung mga pwede mong pagbasehan ng kung anong method yung gagamitin mo. Kung ano yung fit sa problem as well as kung saan ka sanay. Okay? So according to the code, since the code nga gusto niya yung structure natin, yung beam natin will still be serviceable. So si code, meron lang siyang inaalaw na maximum deflection. So kung ito yung beam natin, simply supported, in-apply ng load, nag-deflect like this, yung deflection na yan, nililimit lang yan ni code. So meron lang yan certain value. Okay? So you can refer to codes to know the maximum deflection that they allow. Okay, so if we will try to use the traditional criteria for deflection, we can use this particular table. Past guides may still be used for preliminary design. For selection of beam cross sections, the criteria that may be used are as follows. So ito yung mga selected traditional criteria for deflections that we can use. for preliminary design. So for example, for this particular formula, dapat daw yung ratio ng length ng beam, which is this is the length of the beam, divide mo daw sa total depth ng beam. So kung ito yung beam mo, although still tayo, so ano na lang, gawin ko na lang I-beam. So kung ito yung I-beam mo, ito yung total depth na sinasabi yung D. So dapat daw yung ratio ng length mo ng beam tsaka sa total depth ng beam mo, ng steel beam mo, will always be less than or equal to 800 over Fy, wherein yung Fy naka PSI dapat. So dapat naka US customary units ka dito. So yan yung gagamitin mo for floor beams and girders, fully stress. Okay? So pag ganun yung condition, you are computing the deflection for floor beams and girders that are fully stressed. You can use this criteria, okay, for finding the I mean for ensuring that your structure will not experience excessive deflection. Okay? So for floor beams and girders subject to shock or vibration loads naman, dapat daw yung ratio ng length tsaka nung total depth of the beam cross section will be less than or equal to 20. So in that way, you can ensure that your beam will not experience excessive deflection. So for roof purlins, fully stress except flat roofs, you can use this formula, almost the same as this formula. You just have to change 800 to 1000. So in that way, if you are making sure that the ratio of the length to the total depth of the steel beam will be less than or equal to 1000 over Fy, you can be sure that the steel beam will not experience excessive deflection. Okay, that is according to the past guides, the traditional criteria for for ensuring serviceability of structure. For initial section selection, the required depth may determine using any one of these criteria. Okay, so if you have a specific magnitude of length, meron ka ng length ng beam, and you want to find the the total depth that can ensure that the beam will not experience excessive deflection, you can use all of these formulas. Okay, just substitute the value of L and then compute for T. Yung Fy given naman yan. Okay, so you can use this formula as ano lang, as a preliminary size lang naman. Kasi whenever we design, as we have talked about before from module 1, you need to have preliminary sections. Okay, you must have preliminary sections. So your steel beam must have uh, uh, dimensions initially. Kahit na wala ka pang dinidesign, dapat meron na siyang initial lang naman. Kumbaga dun yung starting point mo. Because as we have discussed, designing is actually an iterative process. Okay? Kumbaga parang trial and error lang siya. As long as you can show that safe yung naging design, it's already okay. As long as safe, napatunayan mo na safe using computation. Napatunayan mo na yung stress less than sa allowable, yung deflection less than sa allowable, etc. etc. Okay? If you will be referring to IBC deflection limit, so IBC stands for International Building Code. So it's an international code, obviously, from the name itself, International Building Code. That is actually one of the code that our local code NSCP usually refers to, the IBC, the International Building Code. The International Building Code provides deflection limits for different beam types subjected to service loads as follows. So ito yung mga makikita nyo sa IBC deflection limits. So if you will be computing the deflection for roof beam supporting plaster ceiling, you can use this formula if you are just computing for the maximum live load deflection, meaning this is just the deflection due to the live load only. Okay? So meaning kung ito yung beam mo, tapos may dinadala siya na load, tapos syempre magde-deflect yan. De-deflect yan ng ganyang magnitude. Dapat daw, yung magnitude nitong deflection na to, due to live load alone, due to live load, wala pang dead load yan. Due to live load pa lang, dapat daw, yung magiging deflection niya due to live load, hindi lalagpas ng L over 360. Okay, wherein yung L is the span of the beam. Okay. So you can see here na on this on this particular criteria, you can see here yung deflection is actually related to the total depth of the beam. So why is that? Bakit naging related yung deflection sa total depth ng beam? Kung naalala nyo sa strength of material or sa mechanics of the formable bodies or as well as sa structural theory, yung sa double integration method, kung naalala nyo, di ba sabi doon, y double prime is equal to m over ei. Di ba? Ayan yung starting point ng ano, di ba, ng double integration method. Yung tapos 'di ba pag din-integrate mo yan twice, makukuha mo yung equation for the deflection, 'di ba? Na naka in terms of ano, EI, may over EI ka diyan. So you can see there, yung deflection is actually related to moment of inertia. And moment of inertia is related to the depth. Kunyari, ang moment of inertia ng rectangle is actually equal to BH cube over 12, 'di ba? So magkakadugtong yan eh. So ano bang nangyayari sa deflection kapag yung moment of inertia mo malaki? Okay? So take note, yung moment of inertia, denominator yan ha. Yung denominator, ano ba nangyayari sa whole fraction kapag yung denominator mo lumalaki? Di ba yung deflection lumiliit, yung y? Okay? So, yun yung gusto nating mangyari sa mga beam natin. As much as possible, lumiit yung deflection. And paano nga natin ulit mapapalit yung deflection? If the moment of inertia is large enough. So, paano mo ba mapapalaki yung moment of inertia? Either lakihan mo yung b or yung h. 'Di ba? Kasi nga I is equal to BH cube over 12 for the case of rectangular section lang Okay? So either laki mo yung B or yung H, lalaki yung I. Pag lumaki yung I, liliit yung deflection. That will be experienced by the beam. Okay? Pero dito sa dalawang to, kung mamimili ka, sino yung lalakihan mo sa kanila? Sino yung mas critical kung babaguhin mo yung dimension niya? Kung titignan mo yung dalawa, B at H, sino ba yung mas magandang lakihan? Nang sa ganun, lumaki yung I ng malaking, kumbaga sino ba sa dalawang to, sa B tsaka H, yung may malaking effect sa magnitude ng I? Obviously yung H. Kasi yung H, kinocube mo pa siya, 'di ba? Kumbaga, kung dagdagan mo ng maliit na dimension yung B, kunyari dinagdagan mo ng 0.1 yung B. So syempre lalaki yung moment of inertia. Pero yung H, kung yung H yung dinagdagan mo ng 0.1, eh yung H mo, pagdating dito, kinube mo pa. So, ilan technically yung magiging increase sa moment of inertia? So, malaki. Kasi kumbaga parang natitriple. Di ba? Parang natitriple yung dinagdag mo. Nagdagdag ka ng maliit on both B at H. Pero yung effect niya sa H, natitriple. Kasi nga, kinukube mo siya dito sa formula. Usually naman sa lahat ng formula ng moment of inertia, parang ganyan naman yung pattern nila. Di ba? Yung total depth, nire-raise mo to a certain power. Square, cube, fourth, etc. etc. So, ibig sabihin lang yan, mas malaki yung effect ng depth, total depth, sa deflection. Di ba? Kung nilalakayan mo yung depth, kahit kakarampot lang yung dinagdag mo sa depth, eh matitriple yan sa formula na to. So, mas magiging malaki yung effect niya sa pag-minimize ng deflection. That's why makikita nyo dito, yung relationship na kinuha is actually the depth, hindi width. Kasi kung deflection ang pag-uusapan natin, mas malaki yung effect ng total depth compare sa width. Okay? So, mas malalim yung mas malalim yung beam mo, ang tendency, mas maliit lang yung magiging deflection niya. Okay, ano? Pag mas malalim to, ibig sabihin mas malaki yung H, tinriple mo siya, sinubstitute mo dito sa formula, ibig sabihin lalaki yung denominator. Eh di lalong liliit yung yung deflection. Okay, that's why makikita mo dito, yung total depth, yung ginamit to ensure that the steel beam will not experience excessive deflection. Okay? So going back to the IBC deflection limit. So yun na nga, kung meron kang beam, in-apply mo ng live load, magde-deflect yan due to the live load. Dapat daw yung deflection na yan will not exceed L over 360. Okay? So kung 10 meters yung 10 meters yung length mo, dapat diyan lalagpas sa 10 over 360. So ilan yun? Nahirapan ako. 3,600 na lang. mm. Para madali lang mag-divide. Kung yung total length mo is 3.6 meters or 3,600 mm, 3,600 divided by 360 is just equal to 10 mm. Kasi mm to eh. Diba? So, ibig sabihin lang yan, yung maximum deflection due to live load alone, alone. Wala pang dead load na kasama yan. Dapat daw equal or less than sa 10 mm. Okay? Kung isasama mo na yung dead load, so may sasalpa ka pa dyan na dead load, So, dahil siyempre magkakaroon ng additional deflection yan kasi may dinagdag ka na load eh. So, dapat daw yung magiging total deflection due to live load and dead load, hindi naman nalalagpas sa L over 240. So, medyo lumaki yung limits nung may kasama ng dead load. Tama ba? Mas malaki yung L over 240 sa L over 360. So, medyo lumaki yung limits. Okay? Yung snow load, syempre, hindi naman applicable sa atin yan. Although yung may wind load naman na may wind load naman na sinabi dito. Pero snow load wala naman tayo dyan. Usually ang tine-check lang naman natin for deflection is dead load, yung effect ng dead load tsaka live load. Okay? So pag ano yan, pag supporting plaster ceiling pa lang yan, na roof beam. Okay? Pag not supporting naman, ito naman daw yung gagamitin. Pag supporting non-plaster ceiling, ito naman. Kung floor beam lang yung check mo yung deflection, ito yung mga gagamitin mo. L360 o L over 360 tsaka L over 240. And yan usually yung ginagamit natin, guys, for checking of deflection. Yan yung limits na ginagamit natin to ensure that our beam will not experience excessive deflection. Kasi nga, pag excessive yung deflection niya, it will affect the serviceability of the beam. Okay, so hindi na siya magmumukhang serviceable. It will impose fear doon sa mga occupants. Kasi ikaw ba naman, makakita ka beam, tas nakalundo na. 'Di ba? Ano yung mentality mo doon? Eh di, kumbaga nasa on the verge of failure na yung beam. So medyo may takot ka, hindi ka na papasok doon sa structure na yon, 'di ba? So, yung deflection naman, hindi naman natin maiiwasan yun eh. We cannot avoid deflection with respect to the structure. What we can do there is limit it. We can limit deflection by adjusting the dimension of the cross-section of the beam. Okay? We can control the deflection by adjusting the dimension of the cross-section. Okay? So, those are the different criteria that we usually check whenever we design flexural members. So all of those criteria are actually included as a provision, code provision inside our local code, which is the 2015 NSCP Volume 1. Okay, so just to summarize everything, the code provisions related to the design of flexural members with respect to flexure, with respect to shear and deflection. So let us just summarize everything on this particular topic. So these are the 2015 NSCP Volume 1 code provisions for analysis and design of beams. Okay, so may just remind everyone that for this module, only doubly symmetric hot rolled eye shapes with compact webs bent about its major axis will be considered and used for analysis and design of beams. So for this particular type of hot rolled eye shapes, the provisions that are applicable are coming from sections 506.2 to 506.3 of NSAP 2015 Volume 1. Okay, so for this particular module lang guys, for discussion lang. For discussion's sake, we just limited our discussion to doubly symmetric. So again, what do we mean when we say doubly symmetric? Doubly meaning double, dalawa. Ibig sabihin, dalawa symmetric. So ano ibig sabihin nun? Symmetric siya with respect to its two axis. Okay, kung meron kang I-beam, may I-beam ka dyan, so may axis siya, major, tsaka minor. Sabihin ng doble symmetric, symmetric siya with respect to this. Sabihin, kumbaga, parang mirror lang niya yan. Mirror niya lang yan. And then symmetric pa siya with respect to this. Parang mirror niya lang to dalawang yan. So, doble symmetric siya. Okay? And then, take note, compact lang. With compact webs lang tayo that are bent about its major axis. So, yung bending ng mga steel beam na pag-uusapan natin dito, dito lang. Dito lang siya nagbe-bend sa major axis, sa x-axis na to. Okay? And meron silang compact web. Okay? So, dyan lang tayo nakafocus. So, pag ganyan yung ano natin, yung steel beam natin or flexural member natin, the particular code provisions that will apply will be found on section 506.2 to 506.3 of NSAP 2015 Volume 1. Okay? For other type, you can use the other provisions, other code provisions of the NSAP. So you can use 506.4 kung ano pa yung mga applicable provisions doon. Kung hindi symmetric, kung hindi double symmetric, tsaka hindi compact yung web. Tsaka hindi nagbe-bend sa major axis. Okay? In analysis and design of beams with W-symmetric hot roll eye shapes blend about its major axis, flexure, shear, and deflection must be considered. So yan nga yung mga kailangan natin check whenever we analyze or design a flexural member. Check natin siya with respect sa flexure, dapat hindi siya hindi siya mag-fail. Quotation, fail. Again, take note what do we mean when we say fail. Hindi siya necessarily as in total failure, as in sira yung member dapat. So when we say fail, ibig sabihin lang nun, yung mga limit states na pinag-usapan natin are no longer satisfied. Okay? So dapat hindi siya mag-fail sa flexure, sa shear, tsaka sa deflection. Simply because yung tatlong yan, sabay-sabay nag-act sa isang flexural member. Okay, may flexion na nararamdaman, may shear na nararamdaman as well as deflection. So yung tatlong yan dapat masatisfy for our design to be proper. Okay, so these are the particular code provisions related to checking on the limit state or on the type of internal effect, which is flexure. So these are the code provisions related to flexure checking. Okay, so in analysis and design of beams considering flexure, the following must be satisfied. So almost similar to the other formulas that we have discussed from the previous modules. Nag-iba lang ng symbol, pero yung meaning parehas pa rin. Ibig sabihin lang yan, yung left side, yung capacity. Yung capacity ng member natin, yung flexural member natin, dapat palaging mas malaki compare sa demand dun sa internal effect na nire-resist nila. Okay, so in this case, since flexure tayo, syempre puro moment ang pag-uusapan natin dyan since flexure tayo. So dapat yung flexural capacity is greater than the flexural demand. Yung moment induced by the transverse load. Yung MU, yan yung nakukuha mo kapag nag-drawing ka ng shear and moment diagram. So kung meron kang applied load dyan na uniform distributed load, meron siyang i-induce na shear and moment, di ba, inside the beam. So yung moment dun, yun yung MU natin. Okay. Yung VMN natin na yan, yan yung flexural capacity ng member natin, which is usually dependent sa dimensions ng flexural section. Kung ano yung section na to, kung ano yung mga dimensions niyan, usually doon nakadepende yung MN. Okay? Yung capacity, yung nominal capacity ng member in resisting flexure. So yung capacity na yun, usually, minumultiply natin ng certain factor. Pag LRFD yung design philosophy na ginagamit natin, minumultiply natin siya sa phi para limit yung capacity niya, para magkaroon ng allowance. Okay? Para hindi natin masyadong ma-maximize yung capacity niya. Just to account for uncertainty sa capacity ng member. Kasi nga, kunyari, ang akala natin ng FY ng section, 250 megapascal, pagdating pala sa actual, 200 lang pala yung capacity niya. So, nagkaroon ng uncertainty sa capacity. Diba? So, mas maliit pala. Mas maliit pala yung capacity niya kaysa sa totoo. Kaysa sa sa na-consider natin sa design. So, magkakaproblema ka dyan. So, in order to avoid that, minumultiply natin ng mga strength reduction factor yung capacity for LRFD. Sa ASD, minumultiply naman natin siya ng 1 over omega. So, ang purpose niyan, same sa purpose nito, to reduce the capacity of the member. Okay? Same lang naman yung effect niya. So, pag ASD, i-multiply mo siya sa 1 over omega. Pag LRFD, multiply mo siya sa phi para lumit yung capacity. Same lang naman yung effect niyan. Parehas niyang pinapalit yung MN. Kasi nga, eto, dinidivide mo. So, liliit. Nagdi-divide ka eh. Usually, yung omega whole number. Katulad nito, for flexure, ang omega ay 1.67. So, you are dividing MN to a whole number. So, malamang liliit talaga yung value ng buong fraction. While dito sa LRFD, yung phi natin usually less than 1. So, every time you multiply a number to a number less than 1, obviously, lumiliit yung value. So, pares lang yung effect nila. Okay? Although sa LRFD, you have to consider na yung mga moment na kinoconsider natin are ultimate. Sabihin yan yung mga naka-factor, yung mga may 1 point. Yan yung mga bending moment due to a load equal to 1.2 dead load plus 1.6 live load. Yung mga may factor, yung may mga amplification. Sa ASD, wala. Wala tayong ginagamit ng mga factor. Dead load, live load lang. Although may iba pang load combination na meron din namang factor. Okay, pero hindi yun yung sinasabi nating factor. Yung factor natin is yung nasa code na mga load combination related to LRFD. Okay? From table 506.1.1 of 2015 NSCP Volume 1, for doubly symmetric eye shapes with compact webs had through the eye shapes bent about its major axis, the following limit states must be considered for flexure. So ito yung mga limit states checks for beams whenever we design it with respect to flexure. Okay, so you can see this on table 506 0.1.1 of NCP. So you can see here, with respect to flange stability, kunyari, we want our flange to be compact. So dapat i-check natin siya sa yielding tsaka sa lateral torsional buckling to ensure that our flange will be compact. Magkakaroon ng ng stable flange yung section natin. Okay? So, kung yung flange naman natin ay non-compact or slender, kailangan natin i-check na limit state ay yung compression flange, local buckling, as well as lateral torsional buckling or yung LTB. Okay? So, itong mga to, different code provisions yung kailangan mong gamitin dyan. Whether yung section mo ay compact, ibang section ng NCP yung gagamitin mo. Kapag yung section, kung yung section mo ay non-compact, ibang section din ng NCP yung gagamitin. Kung slender yung yung section mo, ibang section din ng NCP yung gagamitin. Okay, but then again, for this discussion, we are just limiting our discussion for compact section or for compact flange, for sections with compact flanges. Okay, so for sections with compact flange, ang kailangan lang natin i-check ay yung yielding tsaka yung lateral torsional buckling. Okay, kapag non-compact na or slender, we have to check also, we need to check, instead of yielding, we need to check compression flange, local buckling, kasi yun yung nag-govern kapag non-compact or slender yung compression ng flange with respect to local buckling. Pati yung LTB, syempre. The nominal moment strength for each limit state must be calculated. Since there will be two values to choose from, the more critical limit state must be selected for the analysis or design considering flexure. So if ever we will check the steel beam subjected to flexure with respect to yielding, the nominal capacity is just equal to the plastic moment that we have talked about a while ago. Okay, that's MN, yung nominal, yung plastic moment. That is the nominal moment that we are considering. Okay, and from the previous discussion, we have seen that plastic moment is just equal to the product of Fy, the yield stress or yield strength, and the section modulus. So may extra dito, ibig sabihin, section modulus yan, plastic modulus yan with respect to the major axis of the beam. So take note, just like section modulus, yung plastic modulus, pwede rin siya with respect to dalawang axis. Kasi nga, the beam can bend with respect to the beam can bend with respect to this major axis or with respect to this minor axis. Okay, but then again, we are just limiting our discussion to the two beams bent about its major axis. That's why ZX na lang inilagay natin dito. Pero meron ding ZY, guys. Meron ding ZY. You also have to check that whenever it was mentioned by the problem. Okay. So for checking of compression flange local buckling, these are the corresponding capacities of the beam that have that is critical with respect to compression flange local buckling. So ito yung mga pertinent code provisions that you have to check to get the nominal capacity, to get the nominal moment capacity. Okay? So yung kanina, for yielding yan. Yung nominal moment capacity na makuha natin dyan, for yielding pa lang yan. Okay? So ayaw natin mag-yield yung steel beam natin. So dapat hindi natin siya papa-experience ng moment greater than this plastic moment, which is the nominal capacity for yielding lang. Okay? Kung ayaw nating magkaroon ng compression flange local buckling, ito naman yung mga nominal capacity ng beam natin. Sabihin, ito lang yung maximum moment na dapat i-experience ng beam nang sa ganun hindi maganap yung compression flange local buckling. Okay, so mayroon tayong iba't ibang formula depende kung non-compact yung flange or slender yung flange. Okay? So for sections with non-compact flanges, this is the formula for finding the nominal moment capacity. So the nominal moment capacity for sections with non-compact flanges is just equal to this. So yung kanina, obviously, since nag-yield siya, we can assume compact yan. Compact yung section dito. Kasi nag-yield yung ano mo eh, yung steel beam mo eh. Di ba? Diba yan nga yung ano, yan nga yung purpose ng ano, ng checking whether compact siya or not. Kung kaya niya mag-yield or not. Okay? So, for kung compact yung section mo, we can just use this. Okay? To check its yielding. Kung non-compact yung ano mo, yung section mo, sabihin meron siyang non-compact flange, you can use this formula. Which is just equal to plastic moment minus quantity plastic moment minus 0.7 Fy Sx the section modulus times width thickness ratios. Okay, ratio ng mga difference ng mga width thickness ratio. Lambda is the flange width thickness ratio. Lambda PF is the limiting width thickness ratio. That's just equal to the lambda P kanina. Pero since flange lang yung pinag-uusapan natin dito, nilagyan na natin ng F pa para makita mo na lambda P ng flange yan. Over lambda RF minus lambda PF. Okay, yung lambda RF, limiting width thickness ratio for a non-compact flange. So, yung mga lambda P na yan, yung lambda PF na yan, tsaka yung lambda RF na yan, yan lang din yung kaninang ginamit natin for checking of local stability ng flange. Okay, nilagyan lang natin ng F to indicate na para sa flange na limiting values yung kailangan natin dyan. Since flange nga yung pinag-uusapan natin dyan. Okay, since for non-compact flange nga yan, yung formula na yan. Okay, for sections naman with slender flanges, so if you can remember, sino ba yung mga sections with slender flanges? Yan yung mga may width thickness ratio greater than lambda r. Ito yung mga may non-compact flanges. Yan yung mga may width thickness ratio ng flange uh, 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 less than o kumbaga nasa pagitan ng lambda p or equal tsaka ng lambda r. Ito pala may equal to. Yan. Okay. So for sections with slender flanges, you can use this formula. Mn is equal to 0.9 EKCSX over lambda squared. E is the modulus of elasticity, 200,000 megapascal for steel. Kc, coefficient of slender unsteepened element, which is equal to this, 4 over square root of h over dw. H is the clear distance between flange less the fillet radius for rolled shapes. Okay, so yung H na yan denoted as T in 2004 and in 2004 ASEP Steel Handbook. So, ito lang yan yung H na sinasabi dyan. Kung ito yung I-beam mo, I-beam, yung H na sinasabi dyan ay ito, yung width lang or height lang ng web. Okay? Although sometimes, if merong fillet dyan, yung fillet yung pa-curve na ganito. Yan. Yung sa actual kasi may fillet yan eh. Yan, may mga pa-curve yan na portion dyan. Pag may fillet, ang H lang na kino-consider natin ay ito lang. Naka-less dapat yung fillet radius. Yan. Yan lang yung H natin. Although kung titingin ka sa ASEP Steel Handbook, yung H na binibigay doon, which is denoted as T, naka-less na yung fillet radius. So wala ka nang kailangang intindihin pa. TW, thickness ng web. SX, section modulus with respect sa major axis. Lambda, flange width thickness ratio. Okay, so yung lambda dyan is the lambda F actually, the width thickness ratio of the flange. Okay, so that is checking for compression flange local buckling. Okay, kapag critical yung yung compression flange local buckling. Kung critical naman yung lateral torsional buckling, the checking that we do is with respect to the unbraced leg, that just like what I have mentioned a while ago. Okay, so just if you want our beam to avoid experiencing lateral torsional buckling or LTB, we have to ensure that it will be adequately braced. Okay, so, dapat meron siyang enough brace so that it will not experience LTB, lateral torsional buckling, and we have mentioned that the stability with respect to lateral torsional buckling of a beam is usually dependent dun sa lateral braces. Of course, kung laterally brace siya all throughout the length, mas maganda. Talagang maiwasan mo yung lateral torsional buckling. But again, that is not usually the case for steel beam. Kasi nga sa mga steel beam, kunyari ito yung section or ito yung side view ng isang I-beam na steel beam. Usually yung mga lateral bracing niya is just located at a certain point. Kunyari dyan, dyan, then dito, and so on and so forth. So usually, yung mga lateral supports nila is just located at a certain distance from each other. Okay, so yung distance na yan yung tinatawag natin na unbraced length, yung LB. Okay, yung LB na yan, kung natatandaan yung graph na pinakita ko kanina, parang ganito yung itsura ng graph nun, yung y-axis niya, yung moment capacity, yung x-axis niya, yung unbraced length. Kung naalala niyo yung graph kanina, di ba may point dito, ito. Yan yung LP. Kung naalala nyo, LP. Yan yung LP. Tapos dito meron din point dito, di ba? Yung LR. LR yun, di ba? Tama ba? Kung tama yung pagkakaalala ko. So, yan yung mga limiting magnitude ng spacing na to ng mga bracing to ensure na yung moment capacity according to this graph will be achieved. Okay? So, kung gusto mo ma-achieve nung section yung ano yan, yung plastic moment niya, this is the plastic moment, di ba? According to the graph kanina na pinakita ko. This is the plastic moment. Kung gusto, if you want to ensure that the beam will reach the maximum moment capacity that it can offer, which is equal to the plastic moment MP, you have to make sure that the spacing between these bracings will be equal or less than to LP. Okay, which can be computed to be equal to this. Okay, yan yung LP na tinatawag natin. 1.76 Ry square root of E over Fy. Okay. Ngayon, if you want to ensure naman na magkakaroon ng elastic buckling yung member mo, you can compare the unbraced length to the LR. Okay? Kung naalala nyo, di ba ito yung portion na elastic yung buckling kapag slender, tapos ito naman yung inelastic. So, kung gusto mong malaman kung anong behavior ng beam yung gusto mo, inelastic or elastic, you have to compute for LR. Kung gusto mo ma-achieve pa rin ng beam yung ano niya, yung medyo mataas-taas na moment capacity niya, you have to ensure na inelastic buckling yung magaganap. Okay? Ibig sabihin, dapat hindi ka lalagpas sa LR. Yung spacing ng mga bracing mo, dapat hindi lalagpas sa LR to make sure na magkakaroon ng inelastic buckling and medyo mataas yung magiging moment capacity ng beam mo. Okay? Because according to the graph, kapag yung spacing ng mga bracing is between LP and LR, ito yung mga corresponding moment capacity yan. No? Obviously, mas malaki sila compared dito sa moment capacity kapag yung spacing ay masyadong malaki na. Ito, nandito na. Okay. So this is the formula for LR. 1.95 RTS quantity E over 0.7 Fy quantity square root of JC over SXHO times square root of 1 plus square root of 1 plus 6.76 quantity squared ng 0.76 SXHO over EJC. So, ang haba, di ba? So, don't worry naman kasi usually itong mga naman nasa code naman ito eh. 'Di ba? Usually kapag ang test about sa design, usually you can use the code. You can bring the code to you with you kapag magte-test. And then you can open the code. Usually ganun kapag design yung subject, open code tayo. Or pwedeng gawin yung ng professor nyo, siya na lang magbigay ng mga code provisions. Okay. So sa formula na yan, ito yung mga meaning ng mga formula na yan. Yung LB, obviously, that is the unbraced length. Ito yan, yung spacing between the lateral braces. Okay? Yung LP, that is the limiting laterally unbraced length for yielding limit state. If you want to ensure na mag-yield yung member mo, meaning ma-attain niya yung plastic moment, yung maximum moment na kaya niyang i-offer, you have to make sure na hindi lalagpas sa LP yung yung spacing ng mga bracing niya. Okay, so dapat within this limit. LR is the limiting laterally unbraced length for inelastic LTB limit state. So kung gusto mo ma-achieve pa rin ng beam mo yung malalaking malalaking moment capacity na to, dapat you have to ensure na Yung spacing ng mga bracing nila will be from LP to LR lang. Okay? So, yun yung LR natin, yung limiting laterally unbraced length for inelastic LTP limit state. RY is the minor axis radius of gyration, obviously. E is the modulus of elasticity of steel, 29,000 KSI kapag naka-US, 200,000 megapascal kapag SI. Fy yield strength of the beam material, RTS effective radius of gyration of the cross-section for LTB, which is equal to this. RTS is equal to square root of Iy times 0, square root of Iy times CW over Sx quantity to the 1/2, wherein the Iy is the minor axis moment of inertia of the cross-section, and then CW is the warping constant of the cross-section. Yung pinrovide lang natin dito na formula is the formula for doubly symmetric I sections only, which is equal to this. CW is equal to Iy HO squared over 4, wherein HO is equal to distance between flange centroids, which can be found using this formula, or you can just draw the I-beam and then simply compute for the distance between the centroids of the flanges. So, nasaan yung mga centroids ng mga flanges? So, ito rectangular lang naman yung flange na to, tsaka to. So, ang centroid niya nasa gitna. Ganun din to. So, kunin mo yung distance between them, yan yung tinatawag natin na HO. Okay? So, you can compute that logically, drawing mo na lang yung figure, or you can use this formula. Okay? Which is just the same lang naman kung kukumputin mo yan logically. If this is the depth and the thickness of the flange is equal to TW, so obviously, since yung centroid ng flange ay rectangle lang, so obviously itong distance na to ay half lang ng TF. And ganun din to. Half lang ng TF. Okay? So, equal lang naman yung dalawang yan kasi nga, we are just limiting our discussion to doubly symmetric I section. So, ibig sabihin, symmetric naman siya with respect dito sa major axis. Parehas lang yung nasa top tsaka bottom flange. Okay? So, kung kukunin ko yung magnitude na, yung HO na yan, using this figure, HO is just equal to D minus TF, yung isang to, TF over 2, tsaka yung isang to rin, minus TF over 2 ulit. Or kung pag pinagsama ko yung dalawang yon, T minus times 2 ko na lang TF over 2, that will just be equal to TF. Okay, so same formula lang naman siya dito. Okay, yung D, depth of the cross-section, TF, thickness of the flange cross-section, SX is the major axis section modulus of the beam, J is the torsional constant of the cross-section, which is equal to this, which is for I sections only. 2BF, 2BTF cube plus HT cube over 3. Wherein B is the width of the flange of cross-section. H is just equal to HO, which is the distance between flange centroids. TW, thickness of web cross-section. C is a constant. For doubly symmetric I section, C is usually 1. Okay? So, that the formula for finding the moment capacity with respect to the bracing is actually divided into three cases. Okay, three cases. So for the case 1, wherein the unbraced length is actually less than LP, so meaning mag-yield pa yung ano mo, yung steel beam mo. Kasi ganito yung itsura ng ano, 'di ba, no graph. This is the unbraced length. So itong point na to, 'di ba? Ito nga yung limiting value, which is LP. So kung yung LB mo daw within these limits less than or equal to LP, therefore lateral torsional buckling limit state does not apply, i.e. non-critical, kasi nga it will be more on yielding. Okay? Yung steel beam mo will be behave more on yielding. Hindi siya magla-lateral torsional buckling. Okay, if you will be able to ensure that the spacing between the braces, lateral braces, will be within the limits of LP. Okay? If you will make sure na yung spacing nitong mga lateral braces, drawing ko lang ulit. If this is the elevation view of an I section, tapos ito kunyari yung mga ano niya, mga lateral bracing niya. If you can ensure na yung mga spacing nitong mga to will not exceed LP. Therefore, the steel beam that we have here will behave with respect to yielding. It will more of fail with respect to yielding rather than lateral torsional buckling. Okay? So, ang gagamitin mo dyan is yung formula for yielding, which is Mn is equal to plastic moment equal to Fy Cx kung with respect to major axis bending. Okay? That's the first case. The second case is if the spacing between braces is between LP and LR, meaning kung dito sa graph na to natin titignan, ito yung limiting value ng LR. Kung yung spacing ng bracing mo ay within these limits, okay, nandito sa pagitan na to, which will produce inelastic buckling, inelastic lateral torsional buckling. This will be the formula if you want to compute the moment capacity of the steel beam. Mn is equal to Cb quantity MP minus quantity MP minus 0.7 FYSX quantity LB minus LP over LR minus LP, which must be less than or equal to the plastic moment capacity coming from yielding. Okay? So, yung CB dyan is actually the LTB modification factor, MP, plastic moment of the beam. You can find out that on the yielding limit state. Fy, yield strength of the beam. Sx, major axis section modulus. Lb, unbraced length of the beam. Lp, limiting laterally unbraced length of the yielding limit state. So Lp, yan yung limit state. Yan yung limit natin to ensure yielding. Lr is the limiting laterally unbraced length for inelastic LTB limit state. Lr, ito yan. That is the limit that can ensure that our beam will behave inelastically. Take note, inelastic. We want our beam to be inelastic so that its moment capacity will be as high as this compared to this moment capacity of elastic buckling, elastic lateral torsional buckling. Okay, so that's the second case. For the third case, wherein the spacing between our braces, the spacing between our lateral braces is greater than LR, sorry, meaning the spacing of our lateral braces are larger than LR na. For that particular case, we know for a fact that our beam will behave elastically, and if it will behave elastically, therefore, uh, it will not experience stresses as high as the yield stress. But the repercussion with that or the consequence with that is it will not attain as high as moment capacity as inelastic buckling and in yielding. Okay? So, ganito lang kababa yung ano niya, yung mga moment capacity niya. Ayan lang. Kung ipo-project mo lang siya dito sa y-axis, yan, ganyan lang kababa yung magiging moment capacity niya. Kung yung spacing ng mga lateral braces niya ay equal to LR or greater than pa. So, for that case, the moment capacity of the beam will be equal to this. Mn is equal to FCR Sx, which is less than or equal to the plastic moment. Obviously, hindi naman talaga dapat lalagpas. 'Di ba? Hindi naman talaga dapat lalagpas sa plastic moment. Yung mga makukuha mong moment capacity dito sa inelastic buckling tsaka sa elastic buckling kasi nga maximum yung plastic moment mo eh. Ito, which can be found from case 1, 'di ba? So, dapat talaga yung mga makukuha mong plastic moment dyan, I mean yung mga makukuha mong moment dyan, nominal moment capacity, dapat talaga less than sa plastic moment. Kasi magulat ka kapag yung nakuha mong nominal moment capacity dyan, for example sa case 3, ay larger pa sa plastic moment. So, paano itsura ng graph nun? Pag ganito, parang gumanito yon, di ba? Parang hindi na siya pababa, bigla siyang umangat, di ba? Kasi sabihin, kung ito yung particular length ng nung distance between unbraced length, ito yung corresponding moment niya, which is mas mataas pa sa plastic moment. 'Di ba? So, hindi ganyan. Hindi ganyan. We have to ensure na less than sa plastic moment yung makakompute natin na nominal moment capacity dito. Okay, so parang ano mo na rin yan, less second line of defense mo na rin yan. Kasi para malaman mo kung tama ba yung ginawa mo or not. Diba? Kasi pag nakita mo nga yan, mas malaki pa sa plastic moment, edi ibig sabihin may mali ka. You have to recheck your work. Okay? So, yung FCR dyan, yung MN na yan, is just equal to FCR times SX, wherein yung FCR is the critical lateral torsional buckling stress, which is equal to this. which is equal to CB pi squared E over LB over RTS quantity squared times square root of 1 plus 0.078 quantity JC over SXHO times LB over RTS quantity squared. Okay, E is the modulus of elasticity, LB unbraced length, RTS effective radius of gyration of the cross section for LTB. Na-compute na natin kanina, may formula na tayo kanina dyan. Ganun din yung sa J, torsional constant of the cross section, C constant. For double symmetric eye sections, 1 lang naman yan. And double symmetric eye sections lang naman yung inaaral natin. So, palaging 1 yan yung C na yan. SX, major axis section modulus of the beam cross section. HO, distance between flange centroids. Na-discuss na natin yan. Na-define na natin yan. MP, plastic moment of the beam, which can be found from the yielding limit state. Okay? So, you can see on the formula here, the factor CP. So there is actually a modification, that factor, that CB, as defined here, naka-define ba dito? Ayan, yung CB na yan, which is the lateral torsional buckling modification factor, uh, is actually equal to this formula. Okay? The lateral torsional buckling modification factor CB may be determined from item 2 of section 506.1 of NSCP volume 1, 2015, which is equal to this. Okay, so this is how you can compute for CB. CB is just equal to 12.5 M max over 2.5 M max plus 3 MA plus 4 MB plus 3 MC times RM, which must be always less than or equal to 3. CB is the lateral torsional buckling modification factor. M max is the absolute value of maximum moment in the unbraced segment to be considered. MA, absolute value of moment at L over 4 of the unbraced segment to be considered. MB is the absolute value of moment at L over 2 of the unbraced segment to be considered. MC is the absolute value of moment at 3L over 4 of the unbraced segment to be considered. And RM is the cross-section monosymmetry parameter, which is equal to 1 for doubly symmetric sections. Okay, so ano yung mga binabanggit dyan na M-max, MA, MB, MC? Okay, so balikan lang natin tong sample natin. We have a simply supported beam. Hindi ko na nilalagay yung supports ha. So I-beam lang yan. I-beam, ito yung flange, top flange. Ito yung bottom flange. Yan, ganyan. Tapos may mga lateral bracing yan, di ba? Usually dito, nakalagay at a certain portion lang. So naka-perpendicular yan sa sa paper natin. So ito yung mga spacing niya. Yung tatawagan natin na LB unbraced length. Kasi nga, along that length, walang bracing. Ang may bracing lang dito sa mga particular points na to. Okay, yan yung LB natin. Ngayon, yung CB kasi, nagbabago yung value niyan depende sa particular segment of the beam na kino-consider natin. Yung particular unbraced length na kino-consider natin. Nakadepende doon yung magnitude ng CB natin, lateral torsional buckling modification factor. Kasi nga, if you can remember dun sa video na pinlay ko kanina, di ba ang buckling ng ang buckling ng beam, hindi naman siya nagbabuckle all throughout talaga its length, di ba? Hindi naman talaga ganun, di ba? Kumbaga, kung naalala nyo yung video kanina sa top view, ganito yung itsura ng nung isang beam na nagbuckle. Syempre pa ganyan. Pero kung mapapansin nyo, dito sa portion na to, tsaka dito, hindi naman siya nagkaroon ng lateral torsional buckling. Saan lang siya nagkaroon ng lateral torsional buckling? Yung pinakamalaking torsional buckling. Dito banda sa midspan. Okay? So, unti-unti lang siyang nagla-lateral torsional buckling as you go to the midspan. Wherein the maximum moment occurs. Okay? Kung simply supported siya, tapos uniformly distributed load lang yung dinadala niya. Okay? So, top view yan guys, top view. So, kung gusto nyo ba, ma-imagine pa, balikan yung video kanina, yung may kulay orange na na steel beam. Balikan niyo yung itsura ng section na nagkaroon ng lateral torsional buckling. Makikita nyo, hindi naman siya constantly from this position to this position. Hindi naman ganito yung naganap all throughout the length of the beam. Diba? Banda dito, siguro dito sa portion na to, ang naganap ganito. Kumbaga, hindi siya nagkaroon ng lateral torsional buckling. Or siguro kung nagkaroon man, konting-konti lang. Kunyari pa ganyan lang. Okay, pero habang pumupunta ka dito, pausog ng pausog yung beam yan, parang paganyan ng paganyan siya. Yan. 'di ba? Habang papunta ka sa midspan. And then kung habang papunta ka dun sa kabilang end, pabalik naman siya dito yung itsura ng cross section. Okay, so ibig sabihin, medyo may kinalaman yung ano diyan, yung bracing, yung lateral bracing sa pag-experience ng lateral torsional buckling ng steel beam natin. So, yung CB natin, yung LTB modification factor, must be considered at each unbraced length. Okay, at each unbraced length, which are this. So, kung ilan yung unbraced length mo, ganun karami yung CB mo. Kung may tatlo kang unbraced length, edi tatlo ang CB mo. Okay? So, yung Mmax dyan sinasabi is yung maximum na moment dito sa segment na to. Dito sa segment na to lang. Yun yung Mmax. Yung MA, yan yung moment at this particular location. Okay? Yung MB, yan yung moment at this particular location. MC at this particular location. So, yan, saan ba yung mga location na yan? Yung unbraced length, we just divided it into four equal segments. Okay? First segment, second segment, third segment, fourth segment. So itong first segment na to, this is actually L over 4 from the left end. Itong segment na to is actually L over 2 from the left end. Itong segment na to is actually 75% or 3/4 nung length na to. Okay? So take note, ito lang yung length. Yan lang yung L. Okay, so that is how you can compute the LTV modification factor. It should be noted that the values of CB are different for each unbraced segment of the beam. Thus, CB of each segment should be determined and the most critical value or the least value should be used to determine the design strength of the beam. Okay, so we have to compute the different modification factor, LTV modification factor on each segment, and then we have to we have to choose the least value of the CB. So bakit? Why do we need to choose the smallest? Bakit hindi yung largest? Okay? So kung titignan niyo yung formula kung saan ba ginagamit yung CB, for example here, CB nasa numerator. Okay? So ano siya, directly proportional to FCR. Ano bang nangyayari sa MN sa moment capacity kapag yung CB lumalaki, for example? Pag lumalaki yung CB, yung MN natin, lumalaki din yung moment capacity. Okay? Yung CB, pag linitan mo yan, yung moment capacity natin, lumiliit. Okay? Ano ba yung mas gusto nating dinideclare na moment capacity ng material natin? Yung mas malaki or yung mas maliit? Okay? Naalala niyo pa ba yun? Ikaw, gusto mo mag-declare ng capacity ng isang member. Ano ba yung gusto mong i-declare? Ganito siya kalaki? Kunyari, hanggang 50 kilonewton meter moment yung kaya niya resist or hanggang 30 kilonewton meter na moment lang. Ano ba yung alin ba dyan yung mas gusto mong i-declare na maximum moment lang na kayang dalhin ng steel beam mo? Yung mas malaki or yung mas maliit? Of course, yung mas maliit na lang. Di ba? Mas maliit na lang. Kahit na alam mo na, mas malaki pa rin talaga siya. Mas malaki talaga yung ano niya, yung moment capacity niya. Okay? So, kung naalala nyo pa bakit mas maliit na lang, syempre, kumbaga, low-key lang tayo. Mas gusto natin na i-declare na mahina yung member natin kahit na malakas talaga siya. Okay? Nang sa ganun, kumbaga, ano na natin yun, allowance na natin yun. Allowance na natin yun for the strength of the material. Just in case na hindi talaga yun yung ano niya, yung totoo niyang strength. Kasi syempre, yung loads na i-carry ng material mo is nakadepende sa kung ano yung dineclare mo na ano niya, na strength niya. Kung sinabi mo, ang strength ng member mo, 30 kilonewton, syempre, 30 kilonewton meter, syempre, ang i-apply dyan na load is a load that can produce 30 kilonewton meter na load or larger. Di ba? Hindi naman sa larger. Ang i-apply diyan na load, syempre kung dineclare mo 30 kilonewton meter, malamang nasa 30 kilonewton meter din. Eh, ang problema, paano kapag may uncertainty doon sa load na in-apply? Paano kung hindi naman talaga 30? Baka nasa 40 pala talaga. Okay? Paano yung ganun? Paano kung 40 kilonewton meter pala yung moment talaga na magpo-produce? Paano na? Kung sakali man na 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 dineclare mo yung ano niya, yung sagad-sagad na strength niya, 'di ba? So isipin mo na lang, paano kung ang dineclare mo 50, eh nagkaroon ng uncertainty. So naging 60 yung moment na ina-apply dun sa member. So lumagpas dun sa totoong maximum talaga na capacity niya. So anong mangyayari sa beam mo? Magpo-fail, ba? At least kung lumagpas man sa moment capacity na dineclare mo na to, naging 40 kilonewton yung actual na load na kinere niya, okay lang kasi hanggang 50 nga talaga yung kaya niya. 'Di ba? Dineclare mo lang na 30. Okay, so mas gusto natin mas maliit yung moment capacity kaysa sa mas malaki. Okay? So sa analysis, mas gusto natin pag dinideclare natin yung capacity ng section natin, mas gusto natin mas maliit yung moment capacity. Okay? Kumbaga, mas gusto natin mas low key lang yung section natin. Okay? Huwag nating i-assume na sobrang lakas niya. Kasi mamaya magkaroon ng uncertainty sa load na dadalhin. Siyempre, mamaya lumagpas siya dun sa dineclare mo na moment capacity. Eh di mag-fail talaga yung ano, yung beam mo. Kung max na talaga yung dineclare mo, kumbaga sinagad-sagad mo agad yung declaration mo, di ba? That's why gusto natin yung CB natin, yung list yung pipiliin natin. Okay? So to better understand how to compute CP, the LTV modification factor, let's try to solve this illustrative example 4.3, which uh, which will tackle about how to determine CB, the LTV modification factor of a simply supported beam with lateral bracing at supports and at third points. So the question asks, determine the value of CB that should be used for the given beam shown. The beam cross section is a doubly symmetric section. Okay, so this is the simply supported beam, and as mentioned on the problem, the beam is laterally supported at supports and then at every third points. So meaning it has a lateral support on this point and on this point, and then at every third points, which are here and here. Okay, so as you can see here, if the simply supported beam has lateral bracing on these points that I have pointed out here, therefore the corresponding unraised lengths are this, this, and this. So we have to compute three modification factor, CP, three LTB modification factor for this unbraced length, for this unbraced length, and then for this unbraced length, and then just choose the least CB to be used for the computation of the capacity of this particular simply supported beam. Okay, so the beam is loaded by 2-point loads, which are applied at every third points as well. So we have a P concentrated load here as well as here. So solving for the reactions, it can be easily be computed. So the reaction here will just be uh, shearing to resist the total loads here, which is a total of 2P. So there will be P and P here to be resisted by the supports. So if you will try to draw the shear diagram, it will look something like this. So you have to go up here by a magnitude of P because we have a concentrated load P here. And then along this span, there is no applied load. So therefore, the shear force there is constant. But at this particular point, you have to go down a magnitude of P because there is a concentrated load applied to that point. And then going to this span, there is no applied load, but at this particular point, there is a downward applied force. So you have to go down a magnitude of P. And then at this span, there is no additional or applied load. So you have a constant shear force there. And then at this particular point, you have a concentrated load P from the reaction at the roller. So you will have to go up. So the resulting shear diagram is this. So this is the shear diagram. So as you can see on the shear diagram, there is a portion of the simply supported beam that has no shear force. And that is actually on the middle third. This span here doesn't experience any shear force. Okay, so if we have to draw the moment diagram, so we have to start from zero since there is no concentrated moment applied on the support. and then go linearly from this point to this point, since this is a 0 degree shear force diagram or shear diagram. The moment diagram, the corresponding moment diagram must be 1 degree larger. So it must be 1 degree or first degree, which is a linear diagram. Okay, so on this particular point, there is no shear force, so the magnitude of moment there will be constant. But from this point, you have to subtract the area of this shear diagram. That will result to 0. That will verify that your answer is or your diagram is correct, since there is no moment at the other support, at the roller support. So therefore, the corresponding bending moment must be equal to 0. So the corresponding diagram, moment diagram and shear diagram, will be equal to this. Okay, so we have computed the shear diagram to be able to draw the moment diagram, because as you can remember from the formula of CB, we have to get MA, MB, MC, and as well as Mmax, which are the corresponding moments at every point here on the unbraced length. Okay, so we have to solve CB for each of the unbraced length. So we have to solve three CB here, CB for this span, and this span. Okay, so the resulting moment diagram of the given beam is shown on the image above. So you already saw the moment diagram. It should be taken note that CB values are different for each unbraced segment. Therefore, each segment should be evaluated each for its own value of CB. Consequently, for each unbraced segment, only the part of the moment diagram that includes the unbraced segment should be used for calculation of CB. Okay, so considering the left unbraced segment, which is this is the left unbraced segment. This is the moment diagram on the left unbraced segment. We have to subdivide the moment diagram of the left segment into 4 equal parts and determine the moments at those points. So as you can see, on the formula from the CB, we have to get the the moments at every quarter points. Okay, that's why we have to subdivide the moment diagram into 4 equal parts to get the corresponding moments on each of the quarter points. Okay, so from the given moment diagram, we can see that the maximum moment is equal to PL over 3, which is evident on the moment diagram. This is the maximum moment, the M max, the highest the highest, the point that has the highest y coordinate on this particular diagram. So M max is equal to PL over 3. And then MA on the span, the moment on the first quarter point, which is this, is equal to PL over 12. So how did we arrive with PL over 12? So since we know the magnitude of the maximum moment here, which is equal to PL over 3, and we know that this span is equal to L over 3, therefore we can use ratio and proportion to get the moments at every quarter points. Okay, so using the triangle that we have there, with an altitude equal to PL over 3 and a base equal to L over 3, all we need to do is use ratio and proportion. So L over 3, the base divided by the height, must be equal to the corresponding ratio of this base and this height. So I'll just redraw that here. So it will let this base x and the height is just equal to, or sorry, that the base is just equal to L over 3 divided by 4, since we divided the span, the unbraced length, into 4 equal parts. And then let us just let the height of the triangle equal to x. So the ratio will be equal to this, L over 3 times 1/4 divided by x. Okay, so cross multiplying, we can see that x is just equal to PL over 3 times L over 12. 3 times 4 is equals to 12. And then divided by L over 3. So the 3 here will be cancelled as well as the L. So the remaining coefficients will just be equal to PL over 12. That's why it's PL over 12. So you can compute for the other other moments here on a similar manner. Okay, so the first moment on the first quarter point is the MA, the next one is the MB, and the last one is equal to MC. Okay, so since the beam cross section is double symmetric, as was mentioned on the problem, it was mentioned here that the section is double symmetric, and we know that for sections that are double symmetric, Rm is just equal to 1. Therefore, we can use 1 to represent Rm. Okay, so using this formula and then substituting the corresponding values for Mmax, Ma, Mb, Mc. So we can arrive to this magnitude of Cb for the first unbraced leg. Okay, so you can see here that since the coefficients of MA and MC are just equal to 3, both of their coefficients are just equal to 3. Therefore, you can see that the magnitude of MA and MC can be actually interchanged and will still result to to an answer equal to 1.67, even if you interchange MA and MC, since their corresponding coefficients are just equal. Okay, so there's no harm on mistakenly interchanging MA and MC. Okay, there's no harm in interchanging MA and MC, but there is a corresponding harm if you will interchange MA or MC to MB, since they have a different coefficient. Okay, so always be careful. Always be careful. Okay, so that is the LTB modification factor for the first unbraced segment. And if you will just repeat the the procedure for the middle span, so get the moment at quarter point, first quarter point, second quarter point, and the third quarter point, you can easily see that the corresponding moments on this point, and this point are all just equal to PL over 3, which is the maximum moment. Okay, so we can easily see that the four values here are just identical to each other. Okay, and again, since the cross section is doubly symmetric, we can just use Rm is equal to 1. Then solving for CB, substituting the corresponding values for the formula for CB, we can easily see that the unbraced length, I mean the LTB modification factor for the middle span, middle unbraced length, is just equal to 1. Okay, so meaning if you will substitute this modification factor to the formula of Mn on the previous slides, you can see that the CB has actually no effect, because you are just multiplying because you are just multiplying any number by 1. Therefore, it actually doesn't have any effect to the magnitude of Mn for the computation of the nominal capacity. Okay, so we can actually conclude there something. We can actually conclude something there. We can see that uh, if there is actually a constant moment on the unbraced neck, you can expect that there is no actually an effect with the LTB modification factor, meaning there is no modification that is needed to be applied on that particular span of the unbraced of the beam. Okay, since the bending moment there is just constant. Okay, so there is no uh, variation of the nominal moment with respect to the lateral torsional buckling. Okay, if the span or the unbraced length experiences constant movement. Okay, so lastly, to compute the CB on the right unbraced segment, we will just do the same. Get the MA, MB, MC, and then the Mmax, and then substitute to the corresponding formula. But since you can see on the diagram that the corresponding values of uh, MA, MB, and MC are just equal, although MA and MC again can be interchanged. because again they have the same they have the same coefficient on the formula, which is equal to 3. So you can interchange them. So you can see that if you will try to compute for CB on this right unbrace segment, the corresponding answer will just be the same as this. Okay, so the CB on the right segment of the beam is just equal to 1.67. Okay, so for these values of CB, the LDB modification factor that we have computed, uh, the the CB that we have to use for the computation of MN is the least value, which is equal to 1. Okay, so that's the value of CB that we have to use in order to have a conservative nominal capacity, meaning if we will just use 1 as our CB, therefore we can have a lesser capacity, lesser nominal moment capacity if we will use CB equal to 1 instead of using 1.67. Okay, because if we will use 1.67, therefore the nominal capacity will be 67% larger. Okay, and we don't want to declare that the nominal capacity of our flexural member is as great as 67% higher. Okay, we want to declare the capacity of our flexural beam as small as possible, so that the corresponding loads that will be applied to it will be adjusted accordingly. Okay, of course, if the declared capacity is just say for example is just 50 kilonewton meter, obviously the loads that will be imposed on that particular steel member will not be or should I say the load that will be imposed on that particular member will be based on the capacity, which is 50 kilonewton meter. Okay, so therefore you can expect that the load that will be applied to that will what must be resolved to a bending moment that will not be greater than 50 kilonewton meter, resulting a resulting to a safer design. Okay, because of that, you can assure that the load will not induce a moment greater than the declared capacity, even if the true capacity is larger than the declared. Okay, so with that, you can have an allowance. And we want that. We always want that. For every design that we do, we want to impose an allowance. Okay, for uncertainties, because there is no certain on design. We can just work on uh, 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 estimated values, estimated capacities. Okay, so you can see here the lateral torsional buckling moment capacity is actually greater on this particular portion of the beam, because because the CB on this particular section is actually equal to 1.67. So again, we can conclude another conclusion from that. So we can conclude that the moment capacity of a beam is actually higher on this portion of the beam, on the portion near to the support, to the to the to the support here, than on the midspan. Okay. So we can see there na medyo mas mahina yung beam with respect to lateral torsional buckling dito sa midspan compare dito sa dalawang side na to na mas malapit sa support, which is evident dun sa video na pinakita ko nung nakaraan, kasi nga nakita nyo nung nakaraan dun sa may support kung ganito yung itsura nung beam dito sa may bandang support, pero habang pupunta siya dun sa midspan, yung section ng beam unti-unting nagro-rotate papunta sa midspan. So parang yung susunod na section dyan parang ganito, and then yung next na section banda dito, ang itsura na ng beam parang nakaganito na, hanggang dito sa may midspan medyo nag-rotate na talaga siya, so on and so forth. So ibig sabihin lang na mas critical yung beam on lateral torsional buckling dito sa midspan kung saan nagaganap yung maximum bending moment kaysa dito sa portion na to, kaysa sa portion na to. Okay, so mas critical siya dito sa bandang midspan niya. lateral torsional backlink. Okay? Done on this portion na malapit sa support. So we can draw that conclusion out of the result that we have computed here. Okay? So for more information about CB, the NTB modification factor, you can watch this video from AISC, from the website of uh, AIS. So you can watch this video. Although this is worth 1 hour, so we will skip that. So please watch that whenever you have time.
Yes, yes.
So we will just move on to the next internal force that we also check other than flexure, which is the shear. Okay, so although flexural members are usually more critical with respect to flexure, but still we have to also check the capacity of the flexural member with respect to resisting shear forces. That's why we also have shear provisions on our code. So these are the corresponding provisions related to shear that can be found on our code. In analysis and design of beams, considering shear, the following must be satisfied. So these are just similar to the formulas that I have shown for flexure. So we just provided a different notation or symbol for the capacity as well as for the demand. But the whole concept is still the same. The capacity must be greater than the demand. Okay. So in here, since we are talking about shear, obviously the source of the capacity must be with respect to the shear, okay, as well as the demand. Okay, so Vn there is the nominal shear capacity, Vu is the factored shear load, and Va is the service shear load. Vu is the demand that is used whenever we design using LRFT, which is the trend nowadays because the ASD design philosophy is actually being made obsolete nowadays. So nowadays we are using LRFT to maximize the design that we do instead of using ASD, because as I've discussed before, for LRFD or for ASD, we're just using the strength of the material up to this point, up to the proportional limit or up to the elastic limit. We are just using that capacity of the material so that so that we can ensure that it will behave elastically. Okay, so we are not maximizing the capacity of material whenever we use ASD. Okay, we're just assuming that its capacity is as low as the proportional limit, even though we know that the capacity of the steel beam is actually greater than the proportional limit. Okay, because if you will continue to draw the stress strain diagram, it will look something like this. You will have here a yield stress or yield point as well as the ultimate strength here. So there is actually a very big difference. There's actually a big difference between the proportional limit or the elastic limit and the ultimate. Okay, so we are not maximizing the strength of our material whenever we use the ASD. Okay, that is so that shortcoming is being addressed by the LRFT design philosophy. So in LRFT, we are somehow maximizing the capacity of the material by using unallowable stress on this portion of the stress strain diagram. So thus the stress between the yield stress and the ultimate stress is being used as the capacity of our material if we are using LRFT design philosophy. Okay, so the Vn there for shear is already mentioned a while ago. It is equal to 0.6 FYAW, although for design, we are providing a factor here, which is what we call the web shear coefficient. Okay, so that is what we call the web shear coefficient. So this portion here is the same as what we have mentioned a while ago. So that is the corresponding This is the corresponding allowable stress or tau, because we are talking about shear stress or shear force. That is the allowable shear stress, and this is the shear area. That is the shear area. And then we just multiply it by the a corresponding web shear coefficient to modify the nominal shear capacity. Okay, so for doubly symmetric hot rolled sections with thickness ratio of the web less than or equal to 2.24 square root of E over Fy, we can use this corresponding parameters. So for LRFT, the field that can be used is equal to 1, while the omega can be equal to 1.5, and then the corresponding web shear coefficient can be equal to 1. And then the H here is actually the clear distance between the flange less the fillet radius for rolled shapes denoted as T in 2004 ASEP Steel Handbook. So I already mentioned or defined that H. So the H that is being defined there is actually the height or width of the web alone. So that is H. Although if there is a fillet, you have to subtract as well the radius of that fillet. Okay. TW, thickness of the web, E, modulus of elasticity, Fy is the yield strength of the steel section. Okay. So that is for doubly symmetric hot rolled sections with H over the TW less than this. So that is for less than or equal. So for the case of greater than or equal to or greater than only, in the case of greater than 2.24 square root of E over Fy, we can use this corresponding parameters. So for LRFT, we can use a value of E equal to 0.9, ASD, omega equal to 1.67. And then for the web shear coefficient, we have three cases to check. Case 1, if the width thickness ratio is less than or equal to 1.1 square root of kV over kVA over Fy, we can use CV is equal to 1. But for case 2, wherein the width thickness ratio is in between this and this, we can use CV equal to this. Case 3, if the width thickness ratio is greater than this value, we can use this formula for the web shear coefficient. So wherein the kV there on this corresponding formula corresponds to web plate buckling coefficient. Okay, so the value of that web plate buckling coefficient can be found here. So for unsteepened webs with thickness ratio less than 260, you can use kV is equal to 5. For stiffened webs, we can use a value of kV equal to 5 plus 5 over A over H quantity squared, where it A is the clear distance between transverse stiffeners, and then H is the clear distance between the flange less the fillet radius, so we already defined that H. And then uh, for kV is equal to 5, the A over H there is greater than 3 or greater than 260 over H over TW quantity squared. Okay, so we can for stiffened webs, you can use this formula kV is equal to 5 plus 5 over quantity A over H quantity squared, or this if ever A over H is greater than 3 or greater than 260 over H over TW quantity squared. So what is the clear distance between transverse stiffeners? So let's go back to the I-beam, the elevation view of an I-beam. So this is the top flange, and then this is the bottom flange. So sometimes we are providing there a lateral bracing for local buckling using transverse stiffeners, which are located here in between flanges. Okay, that's actually just another plate that is put here to stiffen the web. Okay, that's why it's called stiffened webs. Okay, so that is the transverse stiffeners. So this is the H that is being mentioned there on the formula. The spacing between transverse stiffeners. Okay. So other than flexure and shear, again, we also have to check the compliance of our design with the allowable deflection specified by the code. So we already discussed this a while ago. So you can use this table uh, to ensure that the deflection will not be excessive, and by ensuring that the ratio of the length and the depth, total depth of the beam will be less than or equal to this value or this value or this value, depending on the corresponding condition. Or you can also use the IBC deflection limitations, which are specified here on the table with respect to the corresponding load that causes the deflection. So if the live load is the only one that causes the deflection, its magnitude must not exceed these corresponding values here. If the live load, if the dead load is added and induce deflection as well, so the total deflection induced by the combination of dead load and live load but must not exceed these values that are mentioned here on the table. And then this is for snow load or window deflection, although we don't usually use that. Usually we just concerned with the deflection due to live load and dead load. Okay, so the corresponding deflection of your design, of the beam that you are designing, must not exceed these values that are mentioned here. Okay, so uh, these are the corresponding procedures for the analysis and design of beams. So since we are already familiar with the different code provisions that we have to check in order for us to analyze or design a beam, so we will now move on to the different procedure or the steps that we have to undertake whenever we analyze or design beams. So we have to start with the analysis of structural steel beams. So these are the steps in analysis of structural steel beams that will just be limited to doubly symmetric hot-rolled eye sections with compact webs bent about its major or strong axis. So you have to remember that we are just limiting our discussion with that. So first, you have to take note of the given data, obviously, and then the design philosophy, whether the question has to use ASD or LRFD. So write also some assumptions that need to be made in order to analyze the given problem. And then after that, check if the section has compact, non-compact, or slender flanges. So you have to use the different formula that we have used a while ago for the compactness of the section components. And you can just see those formulas also on the code. You can just refer to the corresponding section of the code that I have mentioned a while ago. And then after that, depending on the slenderness of the flange, you can use formulas from topic 4.7 to determine the design capacity of the beams. So the formulas that we have mentioned on topic 4.7 is actually used for compact sections. Okay, so for those cases wherein the section is not compact or slender, you have to use other provision of the code. Okay, so first you have to check for flexure. So you have to check the limit states for flexure. You have to check which limit state is the most critical, whether yielding, whether yielding or the lateral torsional buckling or the local buckling is critical. You have to check all of those with respect to flexure checking. Okay, the moment capacity that corresponds to the critical limit state should be the design moment capacity of the beams. So kung sino yung if ever you will check the capacity with respect to yielding, lateral torsional buckling, and then local buckling, uh, the moment, the nominal moment capacity that you will use that that will be resulting on this checking of these limit states must be the least, okay? Because you are analyzing, okay? You are analyzing the given steel beam. You are being asked, what is the strength of this beam? So might as well declare the least moment capacity that you can compute here. Okay, and then after checking for flexure, you also have to check for shear. But then again, that's like what I've said a while ago. For the case of flexural members, usually the flexure is what usually governs. Okay, because obviously it's a flexural member. So the main stress that is being experienced by that member is flexure, obviously. So you can expect the governing check here will always be flexure. Although syempre, you have to check you have to check on case to case basis because you might experience some problem that actually uh, governs for shear or deflection. Okay, so you have to check for shear. You have to get its design shear capacity, as well as you also have to check if the corresponding deflection uh, that are produced by the given steel beam is within the allowable deflection specified by the code. Okay, so you have to check if the maximum deflection of the beam, considering service loads only, and then compare it to the given requirements. If no specific requirements are given, you can use either the traditional criteria that I have shown a while ago, as well as the IPC deflection limits, whichever is more applicable. Okay, so you have to check the flexure capacity, the shear capacity, as well as the deflection limits of the steel beam that you are analyzing. You have to check for the capacity with respect to resisting flexure, and then the capacity with respect to resisting shear force, and then the deflection, the maximum deflection that can be offered by the steel beam that must be within the requirements, within the limitations of the code. Okay, so to better understand how to analyze a structural steel beam, let us try to answer this sample problem. Consider a 9-meter long, simply supported floor beam with hot rolled double 16 by 31 section bent about its major axis, made of ASTM A36 steel, which have which has an Fy equal to 250 megapascal. So we have here a simply supported beam, which have a total length equal to 9 meters according to the problem, and it's actually a W16 by 31 section. Okay, so if you will try to look the cross section of the beam that we are considering here, it's actually a W16 by 31, which is made up of ASTM A36, meaning its Fy is equal to 250 megapascal. Okay, the beam is lateral supported at its supports and third points. So you have a lateral support here and here and at every third point. So meaning of every third points is you just have to divide the whole span into three equal sections or into three equal segments, and then you can see that the beam is actually laterally supported on this part or on this section and on this section. Okay, so if you will try to look at the beam on the top view, it will look something like this. So a it has lateral bracing here at its ends as well as here. Okay, so therefore there is there is there are actually bracing, although we don't know if these are enough to prevent lateral torsional buckling. But the main point there is something that prevents the beam on bending about the minor axis. Okay, so if ever this beam will bend, it will just bend with respect to the major axis, as was mentioned on the problem. It just bent about its major axis. Okay, so dito lang siya nagbe-bend. Diyan lang siya umiikot sa axis na yan, according to the problem. It is subjected to uniform dead load, including beam weight, and live loads applied throughout the entire span. So meron siya diyang uniformly distributed load na kini-carry, which comes from the dead load including the self-weight as well as live loads. So you have to be careful with the dead load computation, since sometimes the question doesn't include the weight of the beam. Therefore, you have to separately compute for the weight of the beam. Although if there is already a given section, all you need to do is find the weight of that corresponding section from the steel handbook and consider that as a dead load on your analysis or design. Okay, so you have to be careful on the computation of dead load. So it is applied throughout the entire span like this. So that is composed of dead load and live load. The question asks for the maximum permissible service load that the beam is allowed to carry, considering flexure, shear, and deflection requirements. For deflections, use IBC deflection limits, use LRFD specifications, and then the ratio of the live load to service dead load is equal to 3. So the question asks for the maximum value of the sum of dead load and live load that this particular beam, W16 by 31, can carry given this corresponding parameters that the question that the question has given here. The location of the lateral bracing, as well as the length and the Fy of the beam, as well as the ratio of the dead load and live load. Okay, so given those parameters, the question asks, what must be the maximum allowed service load, which is just equal to the sum of dead load and live load that the beam is allowed to carry. If you will consider the limit for or the capacity in resisting flexure, shear, as well as the deflection requirements. Okay, so meaning we have to check three cases there. We have to check the capacity of the beam with respect to flexure as well as with respect to shear, and we also need to check the value of the dead load and live load that will uh, that will be imposed on the simply supported beam, and verify that its corresponding deflection uh, is actually within the limits of the code. Okay, so we have to check the capacity with respect to flexure, shear, and deflection. You have to make sure that the allowable stresses allowed by the code will not be exceeded. Okay, we have to find a corresponding dead load and live load that will produce stresses as well as deflection that will not exceed the maximum specified by the code. So that is the goal for this particular problem. So to answer the problem, we have to take note first of the section properties of a W16 by 31 steel section that can be found from ASEP Steel Handbook, since we will use these corresponding parameters on the computation of the capacity of the simply supported beam with respect to flexure, shear, as well as its corresponding deflection. Okay, so you have to take note all of those parameters that you are seeing here. The total depth, the thickness of the web, the width of the flange, the thickness of the flange, the H, which is the width of the web, less the fillet radius, section modulus with respect to X, since we are told that the bending is just with respect to major axis. Then we also need to check the moment of inertia, the radius of variation, and then since as you can see on the formula that are given a while ago, we also need to check for parameters related to the y axis, which are the section modulus, moment of inertia, and then radius of variation, as well as the plastic modulus. So the plastic modulus is actually also given on the ASEP steel handbook. Okay, so you can see that on the steel handbook. Okay, so first, for the analysis, we have to consider first its capacity and resisting flexure. Okay, so we have to find Mn with respect to flexure. Okay, so the first step there is to check for local stability or compactness of the whole section. Okay, so we have to know whether the section is compact, non-compact, or slender. Why? Why do we need to know first whether the section, the W16 by 31, why do we need to check if the W16 by 31 is compact, non-compact, or slender? Simply because for us to know which particular provision of the code we will use to compute for MN. Because you have to take note, there are different provisions related to finding the moment capacity of a section if it is compact, non-compact, or slender. So there are different provisions for different type of section. Okay, so if ever if ever we have found out that the section is compact, therefore we can just use the all of the provisions that we are studying here. Okay, but the bad news there is if we have found out that the section is actually non-compact or slender, we have to use the other provisions of the code. Okay, so you can just refer to the code if ever you will encounter a section that is not compact or slender. You have to refer there how to compute the moment capacity for the non-compact or slender. Because on this discussion, we are just limited to the moment capacity of compact sections. Okay, so how do we say that the section is compact? If all of the section components, the flanges as well as the web are compact individually. Okay, but then again, since we are just considering eye sections which are doubly symmetric, we can expect that the flanges, the top and bottom flanges are just symmetrical or identical. So we just need to check one flange and one web. Okay, so by checking the compactness of the flange, we just have to check its width thickness ratio. But you have to take note that the width that we are talking about here for flange is just half of the total width. Okay, so you have to divide the given width by 2 and then substitute to this formula and then divide to the thickness of the flange. You can find this width thickness ratio of AW16 by 31. And then you have to compare that to the limiting width thickness ratio for yielding. Okay, for compact for compact section. You have to compare that to the limiting width thickness ratio for compact section. Okay, so you just have to substitute the corresponding values and it will result to this. So since the flange width thickness ratio of W16 by 31 did not exceed the maximum width thickness ratio for compact section, therefore we can say that the flange is actually compact. Okay, we can say that the section flanges are compact. Since the width thickness ratio is less than the limiting width thickness ratio for compact section components. We don't need to compute for lambda r anymore since we already found out that the value of lambda is less than lambda t. Since we just have to classify the lambda on three different portion here. Okay, if you can just imagine, if we have a number line here, and these are the limiting values, we just have to check which of these three regions here, which of these three regions will the width thickness ratio will uh, will be included. Okay, we just have to check which of these three regions will that given width thickness ratio will uh, will be included, whether on this region or this region or this region. If the lambda is included on this particular region, therefore, we can say that the given section or the given flange section component is compact. If ever the lambda uh, is plotted here in between lambda p and lambda r, therefore, we can say that it is non-compact. Although on this particular portion, non-compact includes lambda p. Okay, so we have to include lambda p. If ever the lambda is equal to lambda p, therefore we can still consider it as non-compact. But if the width thickness ratio is plotted here, we can consider it as slender if it will be greater than lambda r, greater than or equal lambda r. Okay, so we have found out that the flange is compact. So all we need to do is to check the compactness of the web. So we will just use the same concept. We will just compute for the width thickness ratio, which can be found on the code. and the width thickness ratio for web is just equal to the width of the web, H or T on the ASEP Steel Handbook, divided by the web thickness. And the corresponding answer is equal to this. And then we just have to compute or compare that. We just have to compare that to the limiting width thickness ratio for compact section components, which is equal to this if you will compute it. And we can see that the given width thickness ratio for web is actually included here. It is actually less than lambda p, which is equal to 106. Therefore, we can easily say that the web is actually compact. So since the flanges as well as the web are all compact, therefore, we can say that the whole section is compact. Therefore, we can use the provisions from section 506.2 to 506.3 of the 2015 NSCP Volume 1 code, okay, for the computation of MN. Okay, so we can use all of the code provisions that I have mentioned a while ago that are included on section 506.2 to point 3 of the NSCP Volume 1 code for the computation of the moment capacity of the given beam. Okay, so using that provisions, we can first check for the limit state for yielding. Okay, so this will be the corresponding moment capacity of the given beam for yielding limit state for the scenario wherein the beam already yielded, for the scenario wherein the whole cross section experiences already yield stress. If you can remember on the topics that we have discussed a while ago. So this is the load distribution diagram. I mean the stress distribution diagram for the case wherein the whole cross section already yielded. Okay, so we can see there that the moment capacity of a steel beam that already yielded on the whole cross section is just equal to the plastic moment, which is just equal to the product of Fy and the plastic section modulus. So the Fy is given to 50 megapascal. The section modulus is already found from the ASIP Steel Handbook. So you just have to make sure that your units are consistent. Multiply each of this, and then you can see that the nominal moment capacity is equal to this. Okay. Although you must not conclude that the moment capacity with respect to flexure is already equal to this because we are just checking there the limit state of yielding. So as we have discussed a while ago, we also have other limit state which is the lateral torsional buckling. So we don't want our steel beam to also experience lateral torsional buckling with the same reason for yielding. We don't want our beam to experience yielding as well as lateral torsional buckling. That's why we are checking their capacity with respect to those limit states. Okay, so we are now finished on finding the moment capacity with respect to yielding. So the result, the meaning of our result here is if ever the steel beam will experience bending moment, the maximum bending moment that will ensure that the whole cross section will not experience a stress greater than Fy, the yield stress, will just be equal to 2 to 1.25 kilonewton per meter. If ever there will be a bending moment larger than this that will be experienced by the steel beam, therefore we can say that the stress that will be experienced by the cross section will be obviously larger than Fy. Therefore, the whole cross section will start to yield. Okay, because we all know that if the stress being experienced by the cross section is larger than the yield stress, therefore there will the steel section will start to yield. It will start to experience permanent deformation. Okay, and we don't want that to happen. That's why we will just limit the maximum bending moment that will be experienced by the steel beam to 2 to 1.25. If ever it will govern. Okay, if ever it will govern. But again, we still have a lateral torsional buckling limit state to be checked. Okay, so how do we check the moment capacity for lateral torsional buckling? How do we check the maximum bending moment that will ensure that there will be no lateral torsional buckling that will happen? Okay, so again, for lateral torsional buckling, we are mainly concerned on the bracing, I mean the unbraced length. The moment capacity is actually dependent on the unbraced length. Okay, so we have to compute we have to compare the given unbraced length, which is equal to 3 meters. How did we come up with 3 meters? So since the question said that the beam is laterally supported at every third points here and here, therefore these corresponding unbraced lengths are just equal to 9, which is the total length, divided by 3. Okay, so these are just all equal to 3 meters. Okay, so that will be the unbraced length. So we have to check uh, if that unbraced length falls within this region here, or region here. Okay, if you can remember the graph that I have shown a while ago. Okay, so we have to check uh, whether that unbraced length falls within this region, or within this region, or within this region, for us to be able to know how to compute the corresponding moment capacity. So the limiting values here for the first region is the LP. Okay, if the unbraced length will not exceed LP, therefore we can expect that the steel beam will behave like how it behaved a while ago. It will yield. Okay, it will not experience lateral torsional buckling, but yielding. Therefore, it will still attain the maximum moment that it can offer, which is equal to the plastic moment. Okay, so we have to compute for LP so that we can compare it to LB. Okay, so LP is equal to this formula. Okay, Ry is given on the section properties of W16. E given, Fy given, all we need to do is substitute all of those values here. So the corresponding LP is equal to 1.479, meaning the value of LP here is equal to 1.479. Okay, so if you will try to graph 3 meters on this graph, where do you think 3 meters will fall? Obviously outside LP, because LP is just equal to 1.479, meaning from this point to this point, it is just equal to 1.479. So if I will try to graph 3 meters on this axis, obviously it will fall beyond LP. Although we are not exactly sure if it will fall on this region or on this region. That's why we also need to check LR. Okay, the LR here, which is the limit for elastic buckling. Elastic lateral torsional buckling. This is the limit for elastic lateral torsional buckling. So the formula is somewhat very long. Okay, so the computation for LR is left as an exercise for you. So you just have to find out the corresponding parameters needed here yourself. So just practice that, how to compute those. And if ever you will have a correct answer, the answer that you will get must be equal to this 3.782. So this is equal to 3.782 meters. So with that, if you will try to plot 3 meters here, where do you think 3 meters will fall? Obviously, within this region. The region where inelastic buckling happens. Okay? So according to the code, if the LB falls within LP and LR, the formula for finding MN is equal to this. CB times MP minus quantity MP minus 0.7 FY SX quantity LB minus LP over LR minus LP. Okay? So for this particular problem, the value of CB is equal to 1.01. So you just have to solve CB yourself. So it will just be left as an exercise. You just have to follow the example that we have provided a while ago, and then substitute the value of CB on this formula. So 1.01, substitute the value of MP that we already computed a while ago. MP is equal to 221. So substitute that and make sure that you have a consistent unit. And then this is also MP. Fy is given. Sx given on the properties of the W16. LB and LP as well as LR already given and computed. So all you need to do is substitute on the formula. So the corresponding answer will be equal to this 166.128. So what does it mean? So this just means that for this given lateral bracing spacing, for this given unbraced length, the maximum moment that will ensure that there will be no lateral torsional buckling that will happen is just equal to 166.128. 128 kilonewton meter, or should I say the maximum moment that will ensure that that the the lateral torsional buckling that will happen here will still be inelastic is equal to 166.128. Okay, so there will be a lateral torsional buckling that will happen, but it will be beyond the limit state if the moment induced by the loads will be greater than 166.128. So we have two magnitudes of Mn that we have computed here. The first one is the 221.25, which just means that if the steel beam already experiences 221.25 kilonewton meter of bending moment, it will be on the verge of yielding. Okay, it will be on the verge of experiencing yield stresses or stresses larger than the yield stress. Okay, and then for this case, it just means that the if ever the bending moment that is being experienced by the steel beam is already equal to 166.128, it is already on the verge of yielding as well. Okay, it is already in the verge of yielding as well. It already undergone inelastic lateral torsional buckling, although we can still ensure that it will not yield. But if the bending moment applied will be larger than this, therefore we cannot guarantee that the stresses that will be induced by that bending moment will still be beyond, I mean, it will still be below the yield stress. Okay, so if ever we will have to choose which of these two nominal moment capacities will we consider and declare. So again, how do we choose what particular capacity will we declare? Obviously, the smaller. Okay, so we will just choose the more critical nominal capacity, which is the smaller. Simply because if you will try to imagine it, if you have a simply supported beam, for example, that is being loaded by as a uniformly distributed load, if you can just imagine, as you increase the magnitude of the uniformly distributed load, the maximum moment induced there, that is usually happening on the midspan, the maximum moment being induced as you increase the magnitude of the uniformly distributed load also increases. Okay, so if ever the moment here, the magnitude of the bending moment here is already equal to 166.128, meaning the steel beam is already on the verge of yielding. It already experienced lateral torsional buckling, also, although it is inelastic LTB. But if ever the bending moment already exceeded this value here, therefore we can see that the steel beam will already yield. Okay, it will the cross section will already experience yielding. Okay, which is a failure limit state that we don't want to happen on our beam. Meaning, this particular magnitude of bending moment will not actually be realized. Okay? Hindi na aabot dyan yung bending moment. Kasi sa 166 pa lang, mag-fail na yung beam natin. Paano ba siya aabot ng 221? Kung 166 pa lang, fail na siya, di ba? That's why we have to consider that more critical bending moment. Okay? So with that MN, we can use this formula for LRFD since the question has to use LRFD as our design philosophy. So the MN there, the MN there is already computed, 166.128. The phi or flexure is already given from the code. It is equal to 0.9. Therefore, the declared ultimate moment capacity of our steel beam will just be equal to 149.52. So if ever we will choose a corresponding value of dead load and live load, we have to ensure that the corresponding bending moment that these loads will induce will not exceed 149.52. Okay, so that is how we can compute for the magnitude of the sum of dead load and live load here. We have to compute for a magnitude of dead load and live load that will induce a maximum bending moment here at the midspan, which is usually equal to WL squared over 8 for the case of simply supported beam. We have to make sure that that bending moment that will be induced by these dead loads and live loads will not be exceeding 149.52. Okay, so with that, we have to compute first the magnitude of the uniformly distributed load WU, which is just the sum of the amplified magnitude of this because we are using LRFD. So we have to use the load combination with a factor, okay, with a factor of 1.2 dead load and 1.6 live load. Okay, so we have to compute first the magnitude of this uniformly distributed load WU using this formula. So uh, substituting MU, which is equal to 149 according to this equation that we have computed, we can compute for the magnitude of WU. Okay, so just substitute the magnitude of L, which is equal to 9. MU, we already computed that. So the corresponding answer is equal to 14.767. So that is the ultimate uniform distributed load that will be produced by this corresponding values of dead load and live load. Although you have to take note that that is ultimate, meaning that is the uniformly distributed load resulted from summing up the magnitude of dead load and live load with the corresponding load combination factors 1.2 and 1.6. Okay, so the sum of this 1.2 dead load, 1.6 live load is equal to W, which is equal to 14.767. Okay, so since the problem said that the ratio of the live load and dead load is just equal to 3, therefore we can say that WLL is equal to 3WDL. So we can substitute 3WDL in place of WLL here. So therefore you can say that the only unknown here is WDL. So solving for WDL, WDL is equal to this. Multiply that to 3 since live load is just equal to 3 times the dead load. Multiply that to 3, you can already get the corresponding live load. But the question asks for the maximum permissible service load that the event beam can carry. So therefore, we have to add this to get the permissible service load. Because when we say permissible service load, it is just the sum of the dead load and live load. So just add this arithmetically. So the corresponding answer is equal to 9.845 kilonewton per meter. So meaning the magnitude of the sum of this dead load and live load that will ensure that the steel beam will not fail with respect to yielding or torsional or lateral torsional buckling must be equal to 9.845 kilonewton meter. So that must be the maximum value of the sum of the dead load and live load that you will apply on this beam to ensure that there will be no limit state that will be exceeded or that will not be satisfied. Okay, so that is how you analyze a flexural member with respect to flexure. Okay, so with respect to flexure pa lang yan, yung mga kinompute natin na yan. Okay, so the question asks for checking with respect to flexure as well as for shear and deflection effects. Okay, so we just have finished the checking with respect to flexure. So we still have to check the capacity of the beam in resisting shear. Okay, so we also have to check its capacity in resisting shear in addition to its capacity in resisting flexural stresses. Okay, so we have to compute the corresponding dead load and live load that will produce a shear force that will not exceed the allowable stresses specified by the code. So we have to make sure that the nominal capacity of the W16 steel section will not exceed the ultimate shear forces that will be induced by these dead loads and live loads. So therefore, we have to check also the capacity of the steel beam with respect to resisting shear. Okay, so for the analysis of a steel beam in resisting shear, for us to find its capacity in resisting shear, uh, if you can remember the corresponding code provision, we have to check its width thickness ratio of the web simply because, as I have mentioned a while ago, shear stresses are mostly resisted by the web. Okay, if you can remember what I have said a while ago, if this is the if this is the I beam, most of the shear stresses are actually being resisted by this part of the I beam. Mostly by the web. Okay, so we have to check the capacity or the local stability first of the web to know if it is compact, non-compact, or slender. Okay, so for the local stability of the web, we have to check its corresponding width thickness ratio and compare it to this limit here. So as we have computed a while ago, we already computed the width thickness ratio of the web. If you don't remember, okay, so let's just go back a few slides. So we already computed here the width thickness ratio of the web, which is this. Okay, so it is equal to 47.329. So we just have to compare that to this limit here, which is equal to 63.357. And since the width thickness ratio is less than this limit, therefore, we can use a value of P equal to 1 as well as a value of CV equal to 1. Okay, if you can, if you will go back to the given code provision a while ago, uh, it gives you a choice, or I mean, it gives you certain provisions to know what particular value of V and CV that you can use for checking of the shear capacity of the beam. Okay, so since we already found out that the given beam is already included on this limitation, therefore we can already use the value of V equal to 1 and CV equal to 1 as well. Okay, so determining the shear strength of the given beam, we all know that the formula for nominal shear capacity of a steel beam is equal to this. So we have to find out first the web area or the shear area, which is equal to this. So that is just equal to the product of the total depth T and the thickness of the web equal to TW. So we just have to multiply D and TW, which are already given on the section property of W16. So multiply them, you will find the web area or the shear area. So just substitute the corresponding values here on the shear capacity of a steel beam. Substitute the value of Fy at AW, which is already computed here, as well as the value of CV, which is just equal to 1. And make sure that your units are consistent. So the corresponding shear capacity, nominal shear capacity, will just be equal to 422.91 kilonewton. And that nominal shear capacity multiplied by the strength reduction factor, which is equal to 1. So meaning there is no reduction on strength at all with respect to shear if the width thickness ratio is within these limits. Okay, so the ultimate shear force that will be produced by dead loads, by these dead loads and live loads, must be equal to 422. Okay, must be equal or less than 422.91 kilonewton. Okay, so therefore, if we will try to find the corresponding maximum shear force that will be induced by a uniformly distributed load, we can easily see that maximum shear force that will be induced by a uniformly distributed load, if we will try to draw the shear diagram of this given loading, we can easily see that the maximum shear force is actually acting at the support. Okay, which is equal to, if we will try to compute that magnitude of shear force in terms of WU, if this is L, what is the corresponding reactions here? Okay, so the corresponding reactions there is equal to WL divided by 2, because the load here will just be distributed equally on this support and on this support. So meaning the shear force here is just equal to WL over 2, which is equal to this. Okay, so the computed shear force here must be equal at least to the given demand that will be imposed by the dead load and live load that we will apply here using the factored load combination, the 1.2 dead load and 1.6 live load. Okay, so if we will try to compute WU using this formula, substituting the value of VU, which is equal to this, and then computing for WU, we can arrive to this formula. So that is the magnitude of this WU that resulted from this load combination, 1.2 dead load plus 1.6 live load. So since the ratio of the live load and dead load is already given, we can express this in terms of the live load. So WL is just equal to 3WDL, and then substitute 3WDL in place of WLL here. So the remaining unknown is just equal to WDL. You can compute for WDL, which is equal to this, and then multiply that to 3. You can find the WLL. Okay, but that is not the answer already because the question asks for the maximum permissible service load. So we must find the sum of this dead load and live load. So their sum is equal to 62.563 kilonewton per meter, meaning the corresponding dead loads and live loads here that will induce a shear force here, which is equal to 422.91, has a sum equal to 62.653. Okay, which is uh, less than this value. Okay, so if you will try to choose which of this value 9.845 versus 62.653 is more critical, which do you think is more critical between the two, the 62.653 or the 9.845? Okay, so which of the two conditions, a sum of dead load plus live load equal to 9.845, or a sum of dead load plus live load equal to 62.653, which of the two conditions will be more critical? Okay, so with respect to this, which we computed from checking the flexural capacity, this just means that if the applied load, dead load plus live load, is already equal to 9.845, therefore the steel beam will already fail in flexure. Okay, it will already fail in flexure. Therefore, it will not actually uh, experience a load as high as 62.653, simply because for a magnitude of 9.845 kilonewton per meter load, it already failed with respect to flexure, which we have computed here a while ago. Okay, so therefore between the two, the more critical is obviously the lower. Okay, the lower load. Okay, although we still need to check one last uh, code provision, which is about the deflection. Okay, so we have to find out a corresponding dead load plus live load that will induce deflections that will be within the limits of the code. Okay, so considering the deflection requirements of IBC for floor beams, which states that the maximum live load deflection, live load alone, must be equal or less than 1 over 360 of the span length, as well as the maximum dead load and live load deflection must be less than or equal to 1 over 240 times the span length. Okay, so we have to make sure that the dead load and live load will induce a live load deflection alone, not greater than 1 of L over 360, as well as a dead load plus live load deflection not greater than L over 240. So we have to make sure that the dead load here will not exceed the given load here that will not produce a deflection larger than the allowed by the code. So we have to compute a dead load plus live load that will make sure that it will not induce a deflection larger than what is specified by the code. Okay, so for a simply supported beam with a uniformly distributed load, as you can remember from structural theory, if you have a simply supported beam loaded by a uniformly distributed load, according to structural theory, the maximum deflection that will be induced by that load will occur at the midspan equal to delta, which is equal to this formula. Okay, which is equal to the product of 5W L to the fourth over 384 EI. Okay, for the moment of inertia, we just have to use Ix since the beam is bent about the major axis as was mentioned on the problem. Okay, so for checking the deflection limitation with respect to the deflection induced by live load alone, we can use this formula. So we can check what is the magnitude of the live load that will produce a deflection equal to L over 360 or 9,000 over 360, because the span length as was given on the problem is equal to 9 meters. Okay, so meaning according to the code, the allowable deflection that will be induced by live load alone must not exceed 25 mm. Okay, so meaning if we will try to compute the deflection due to this applied load from dead load and live load, it must not induce a deflection greater than 25 mm. So we will just have to find what is the magnitude of the live load that will not induce a deflection greater than 25 mm. So we will just back solve everything here. Substitute 25 here, and then the corresponding value of E and I as well as L. You can find the value of W, which is equal to this. Okay, but that's for the case of live load alone deflection. We also have to check the code requirement for the maximum deflection for the combination of dead load and live load. So according to the code, the deflection due to the combination of dead load plus live load must not exceed L over 240, which is equal to 37.5 mm. Okay, so by back solving, what is the magnitude of W that will induce a deflection equal to 37.5 using this formula, we can see that its value is equal to 13.695. But you have to take note, this is equal to dead load plus live load. Okay? That is not equal to dead load or live load alone. That is equal to the sum of dead load plus live load. So we have to compute the individual value of dead load and live load. So how do we compute that? We can use the given ratio provided by the code. So if you will express that again with respect to LL, WLL is equal to W 3WTL. Substitute 3WDL in place of LL here, and then solve for DL. You can compute for DL equal to this, and then multiply it to 3. You can compute for the magnitude of LL equal to 10.272, which is larger than the LL that we have computed here. So which of the two will be used, the larger or the lower? So again, always choose the lesser value. Okay, for analysis, always choose the lesser value. So therefore, the dead load that will be induced here, that will ensure that the deflection that it will produce will not exceed the allowable deflection by the code, is equal to 3.424, and the live load that must be imposed here that will produce deflection that will not exceed the allowable deflection allowed by the code is equal to 9.13 because it is the lower live load. Okay, so their sum is equal to 12.554, which is again greater than the governing load a while ago for flexure, which is equal to 9.845. Okay, so still we can see that the load from the flexure checking will still govern. Okay, because it is the magnitude of the dead load plus live load, which is the lowest between the three checking from flexure, from shear, and from deflection. Okay, so therefore, among the three, the most critical is the failure with respect to flexure. Okay, because the load that will be imposed here, even if it is still as low as 9.845, will already produce a failure with respect to flexure, meaning the flexure already governed, which is expected. Flexure is usually the governing checking that is usually governed for flexural members, obviously. Okay, so therefore, the correct answer for this particular problem is equal to 9.845. That is the maximum permissible service load, which is equal to the sum of dead load and live load here, that can be applied to the given steel beam for this particular question, that will ensure that uh, it will not violate any of the limit state for flexure, shear, as well as deflection. Okay, so that is the answer for this particular problem. So if ever you want to apply a load on this particular steel beam, you have to make sure that it will not exceed 9.845, because if it exceeds 9.845, you can expect that the steel beam will already fail with respect to flexure. Okay, that is the first failure that will be experienced by a flexural member. Failure due to flexure. Okay,